Hello there, and welcome to Science for Sleep, where curiosity gets cozy, the universe slows down, and even the most dramatic stars are invited to speak in a softer voice. Tonight, we are drifting toward one of the strangest and most beautiful objects in our galaxy, a star system known as WR104, sometimes called the pinwheel star, because it appears to draw a near-perfect spiral in the dark. Now, that already sounds a little suspicious, doesn't it? Stars are supposed to shine, burn, explode, hide behind dust, and occasionally make astronomers spill coffee on important notes. They are not usually expected to sit thousands of light years away and draw neat spiral patterns as if the sky had given one of them a glowing paintbrush and said, "Go on then, make something elegant." Yet WR104 seems to do almost exactly that. It creates a bright, curling structure of dust, winding outward from its centre like a slow cosmic Catherine wheel, or like one of those little garden sprinklers that spins in the summer while everyone pretends not to step directly into it, before immediately stepping directly into it. And before we go too far into this quiet spiral, I would love to know where you are listening from tonight. Are you tucked away somewhere already dark and still? Is it late evening where you are, or morning, or that strange in-between time when the world feels half awake and the kettle seems to be doing most of the thinking? There is something fitting about exploring a star that turns and turns, while each of us listens from our own small turning place on Earth. One planet, many rooms, many clocks, many little pools of lamplight, all looking in imagination toward the same distant point in Sagittarius. If you find this journey soothing or interesting, or simply a gentle way to let the day loosen its grip, I would be ever so grateful if you gave the video a like and maybe subscribed. It helps this calm little corner of science reach other tired minds who might enjoy a peaceful wander through the universe, and, as always, I do hope the story's interesting enough to keep you company, but not so exciting that it keeps you wide awake. Although, to be fair, when the subject is a massive star drawing a spiral with dust while possibly preparing for a dramatic future, the universe is not exactly making sleep easy for us. It does have a flair for presentation, so settle in, let your shoulders drop, and imagine the night sky not as a flat black ceiling, but as a deep field full of hidden motion. Stars are not fixed lanterns. They move, they orbit, they shed material, they tug on one another, they blow winds so powerful that our ordinary idea of wind, the kind that rattles a window or turns an umbrella inside out, feels almost comically small. Around WR104, the winds are not breezes, they are floods of stellar material rushing out into space at enormous speeds, carrying carbon-rich gas from a dying massive star and meeting the wind of a nearby companion. Where those winds collide, something unexpected happens. Dust forms. Oh, that may sound simple at first. Dust is familiar. Dust is what gathers on shelves the moment you finish cleaning them. Dust is what appears under the bed as though it has been quietly organising a small civilization. But cosmic dust is different. It is made from tiny grains of material, often rich in carbon or silicates, the kind of stuff that can later help build planets, comets, atmospheres, and eventually perhaps even living things. Dust is not just mess in space. Dust is part of the universe's recycling system. It is one of the quiet ways stars hand their material back to the galaxy. Still, WR104 presents a puzzle. Wolf-Rayet stars are not gentle objects. They are massive, evolved stars that have already lost much of their outer layers. They are hot, bright, and intense. Their radiation is fierce enough that you might reasonably ask how dust could form anywhere near them at all. It is a bit like trying to make a snowflake beside an open oven, and yet there it is. A spiral of warm dust glowing in infrared light, curling outward from the hidden central stars with surprising order. The explanation begins with partnership. WR104 is not just one star sitting alone. At its heart is a pair of massive stars orbiting each other. One is the Wolf-Rayet star, stripped down, powerful, and throwing off a carbon-rich wind. The other is a hot OB-type companion, also massive, also producing a strong wind of its own. These winds crash together between the stars. The collision compresses the gas, creates a dense region, and in that protected, compressed flow, dust can begin to form. Then, as the two stars orbit, the dust is carried outward, and the rotating motion shapes it into a spiral. A useful way to picture it is to imagine a garden sprinkler again, but a very strange one, set in space, made of two enormous stars, spraying not water but newly formed dust. As the system turns, the outflow traces a curve. The dust does not stay still. It expands outward while the source keeps rotating, and the result is a spiral that looks almost too neat to be real. But it is real, and that is part of the charm. The universe does not always choose chaos when it has the option of geometry. When astronomers first resolved the pinwheel around WR104, it was a remarkable moment because the structure was not just a vague blur or a loose cloud. It had shape. It had repeated arcs. It showed motion over time. The spiral appeared to rotate as the binary system orbited, and by watching it carefully, scientists could connect the visible pattern to the hidden dance of the two stars at the centre. That is one of the lovely tricks of astronomy. You cannot fly there and watch the stars close up. You cannot set a little camera beside them, politely ask them to repeat the last 8 months, and adjust the focus. Instead, you study light. You compare images. You measure spectra. You watch tiny changes across years. Slowly, the system gives away its secrets. WR104 sits in the direction of Sagittarius, a part of the sky rich with the crowded glow of the Milky Way. Sagittarius points us toward the central regions of our galaxy, where stars gather thickly, dust clouds overlap, and the background can become so busy that finding one specific object is a bit like trying to hear one soft voice in a full train station. That makes the clarity of WR104's spiral even more striking. Out there, among the dense star fields and obscuring dust, this system has managed to carve a pattern that astronomers can recognise, model, and follow. The name WR104 is practical rather than romantic. The WR stands for Wolf-Rayet, named after the astronomers Charles Wolf and George Rayet, who identified this class of unusual stars in the 19th century. Wolf-Rayet stars are rare, short-lived, and important. They represent a late stage in the lives of very massive stars, the kind of stars that live fast, burn through their fuel with astonishing speed, and end their lives in spectacular ways. Our sun is steady and patient by comparison. It has been shining for billions of years and has billions more to go. A massive Wolf-Rayet star is more like a candle made of fireworks. Bright, hot, unstable, and not built for a quiet retirement. That short life is part of why WR104 draws attention. It is not only beautiful. It is also a clue to what happens near the end of a massive star's life. Stars like this may eventually explode as supernovae. Some Wolf-Rayet stars have been considered possible sources of gamma-ray bursts, which are among the most energetic explosions known. That is where WR104 gained, in some corners of the internet and popular science, a more dramatic reputation. Because if a future gamma-ray burst were aimed directly toward Earth from a nearby system, that would be, scientifically speaking, not ideal. It would be the sort of thing one might prefer the universe not put on the calendar. For a while, the beautiful face-on appearance of WR104's dust spiral raised a question. If we are looking almost straight down the axis of the spiral, could we also be looking down the rotation axis of the stars? And if one of those stars someday produced a gamma-ray burst, could that beam be pointed toward us? It was an understandable concern because the spiral looked almost like a target. The sky, being very good at unsettling visuals, had arranged dust in a way that invited the human brain to say, "Is that looking at us?" More recent work has brought a calmer answer. Observations using Keck instruments suggest that the actual orbit of the two stars is tilted significantly away from our line of sight, by something like 30 or 40 degrees. That means the system is not as neatly aimed at Earth as the pinwheel image once made it appear. This does not remove every scientific question. In fact, it adds new ones, because if the dust spiral looks face-on but the stellar orbit is tilted, then astronomers have to understand how those two pieces fit together. But for anyone lying awake worrying that WR104 is a cosmic arrow pointed directly at the planet, the news is reassuring. The star is fascinating, not a bedtime emergency. And that distinction matters. Space can be dramatic without being personal. The universe is filled with things that sound terrifying when described quickly. Black holes, supernova, neutron stars, gamma-ray bursts, giant molecular clouds, stars tearing off their own outer layers, galaxies colliding in slow motion. Yet most of these things are far away, spread across huge timescales, and best understood not as threats waiting around the corner, but as processes that make the universe what it is. WR104 is not a villain twirling a dusty moustache in Sagittarius. It is a rare stellar system showing us how massive stars lose material, how binary partners shape each other's surroundings, and how order can appear in the middle of extreme physics. There is something deeply satisfying about the spiral itself. Spirals show up all over nature. We see them in seashells, hurricanes, galaxies, sunflower seeds, and the way water drains from a sink when it is feeling theatrical. They appear whenever growth, rotation, and motion combine. In WR104, the spiral is not alive, not planned, not drawn by intention, but it still carries that familiar shape. The stars orbit. The dust flows outward. The pattern records the motion. It is a natural diagram written in space. That is one reason WR104 makes such a good subject for a quiet night. It lets us hold two ideas at once. On one side, the system is extreme. These are massive stars, powerful winds, hot radiation, violent collisions, future explosions. On the other side, the image is graceful, almost gentle. A spiral turning slowly from our point of view, unfolding over months traced in warm dust. It is like finding careful handwriting on a storm cloud. The physics is fierce, but the pattern is calm enough for the mind to follow. As we begin, it helps to remember that astronomy is often the art of learning from what cannot be touched. WR104 is far beyond any spacecraft, far beyond human travel, and far beyond the reach of anything except observation and imagination. Yet from Earth, using telescopes, careful timing, and instruments that separate light into its hidden details, scientists have learned that the spiral turns with the orbit of the stars. They have measured speeds, angles, and periods. They have built models to explain the dust. They have revised old assumptions when new data arrived. That is science at its best. Not a single answer nailed forever to the wall, but a careful process of looking again and then looking better. You might think of WR104 as a clock, though not the tidy kind with numbers and hands. Its orbit gives it a rhythm of about 8 months. Each turn of the central pair sends another curve of dust outward. The spiral becomes a record of time passing around the stars, not time measured by a wristwatch or a phone, but time written in expanding material. One loop, another, each one drifting farther from the centre. In a way, the pinwheel is the system's memory. It shows where the dust has been, how the stars have moved, and how the winds have shaped the space around them. That idea is useful because so much of space is too large or too slow for us to witness directly. We cannot watch a massive star live and die from beginning to end. We cannot see a nebula form in a single evening, unless the evening happens to last several 100,000 years, which would be inconvenient for snacks. Instead, we look for structures that preserve motion, a spiral around a binary star, a shell around a supernova remnant, a stream of gas pulled from a galaxy. These shapes are not decoration, They are evidence. They are the handwriting of forces. WR-104's handwriting is unusually neat. That does not mean simple, though. The central stars are unresolved in many images, hidden inside the glare and dust. The winds are complex. The dust formation is still an active puzzle. The newer tilt measurements raise fresh questions about how the spiral geometry relates to the stellar orbit. Like many of the best objects in astronomy, WR-104 answers one question, and then quietly places two more on the table as if saying, "Since you're here, perhaps you would like to think about these as well, and we will, gently." There is no need to rush through a system that has been turning for far longer than any human lifetime. We can take our time with it. First, we can place it in the sky, in the rich direction of Sagittarius. Then we can understand what a Wolf-Rayet star really is, why it is so hot and so stripped down, and why it throws such powerful winds into space. After that, we can bring in the companion star, because WR-104's spiral is not a solo performance, it is a duet, though perhaps the loudest duet imaginable. Two massive stars both blowing material outward, their winds colliding between them, creating the dense conditions where dust can form. From there, the spiral begins to make sense, not as magic, not as a drawing, not as a message, but as motion made visible. The stars orbit, the dust expands, the pattern curls outward. A rotating source plus an outward flow equals a spiral. That simple explanation is comforting, but the details are where the wonder lives. How does dust survive? How does it grow? Why does the spiral look so smooth? What does the tilt mean? What might happen when the Wolf-Rayet star reaches the end of its life? And how do scientists separate real danger from dramatic headlines when talking about gamma-ray bursts? These questions are waiting for us, but there is no hurry. For now, picture the system from a comfortable distance. A dark field of stars, the crowded glow toward the centre of the Milky Way. Somewhere in that direction, hidden from ordinary sight, two massive stars circle each other. Around them, their winds crash and fold. Tiny grains form in a place where they almost seem impossible. Those grains drift outward, warmed by starlight, glowing in infrared, arranging themselves into a spiral that turns like a slow wheel in the night. It is strange to think that something so violent can make something so orderly. But the universe does that often. Gravity can turn a collapsing cloud into a disk. A shock wave can compress gas into new stars. A dying star can seed space with the ingredients for future worlds. WR-104 belongs to that same family of contradictions. It is dangerous in the way massive stars are dangerous, not because it is coming for us, but because its physics is powerful. It is beautiful in the way natural patterns are beautiful, not because they were designed for us, but because our minds are very good at recognizing order when light finally carries it home. To find WR-104 in the sky, at least in the imagination, we begin by turning towards Sagittarius, one of the richest and busiest regions of the Milky Way. It is the direction where the galaxy seems to thicken, where the night sky is not just sprinkled with stars, but layered with them, folded with dust, crowded with clusters, and crossed by dark lanes that hide as much as they reveal. From Earth, Sagittarius sits along the bright band of the Milky Way, close to the direction of the galactic centre, so when we look that way, we're not looking out into a quiet suburb of space. We're looking through a crowded city of stars. That is part of what makes WR-104 feel so well hidden. It is not resting in some empty, isolated patch of darkness where a telescope can simply point and say, "There it is." It lies in a region where the view is complicated. There are foreground stars, background stars, thick curtains of interstellar dust, glowing gas, and the general visual confusion that comes from looking through the broad disk of our own galaxy. If the night sky were a calm pond, Sagittarius would be the part where someone had tossed in a handful of pebbles, stirred the water with a stick, and then asks you to find one particular reflection. Astronomers, thankfully, are very patient people, or at least very good at pretending to be patient while their computers process data. To the unaided eye, Sagittarius is already a place of stories. Many people know it as the Archer, though in modern sky watching, it is often easier to find the smaller pattern inside it, the famous teapot shape. Once you know that teapot, you can imagine steam rising from its spout, and that steam is the Milky Way itself, lifting upward as a pale band of starlight. It is a charming image and unusually useful. The sky gives us an Archer, and we turn him into kitchenware. Humans are nothing if not practical when trying to remember constellations. Somewhere in that broader direction sits WR-104, far too faint and obscure to be admired directly with the eyes. It is not the sort of star you can point to from a garden and confidently show a friend. Even with a backyard telescope, it does not simply reveal its famous spiral like a little glowing shell. The object is distant, surrounded by dust, and its most revealing light comes in infrared wavelengths, the kind of light our eyes cannot see. So WR-104 is not hidden because it is small or unimportant. It is hidden because space is deep, dusty and selective about what it lets through. This is one of the first useful ideas to settle into. The universe is not equally transparent in every direction. Dust in space is not like a thick wall, but it can still absorb and scatter visible light. It dims stars, it reddens them. It makes distant objects appear softer, fainter, or sometimes invisible to ordinary sight. In the direction of Sagittarius, this matters a great deal because we are looking through the plane of the Milky Way, where dust and gas are plentiful. If visible light is a person trying to cross a busy room politely, infrared light is the one who knows a side door. It can pass through dust more easily, and that is why infrared astronomy is so important for studying objects like WR-104. When astronomers turned high-resolution infrared techniques toward this system, they found something extraordinary. Around the central stars was a spiral plume of dust, not a random blob, not a vague haze, but a structure with repeating curves. The dust appeared to wind outward from the centre in a form that looked almost like a pinwheel. It was not a drawing, of course, and not a solid object. It was material flowing outward through space. But because the source of that material was rotating, the outflow took on a spiral shape, leaving a visible record of motion. In a still image, it can look like a frozen ornament. In reality, it is more like a moving pattern caught mid-turn. The word pinwheel is helpful because it gives the mind something familiar to hold. Imagine a small paper pinwheel in a gentle breeze. The blades turn around a centre, and you can instantly see the relationship between rotation and shape. WR-104 is not built like that, but the comparison points in the right direction. Its spiral is produced by two massive stars orbiting each other, with their powerful stellar winds colliding and creating dust that streams outward. As the stars circle, the dust is not released from one fixed point in one fixed direction. It is carried around by the orbital motion, and so the expanding material traces a curl. There is a quiet satisfaction in that explanation, because it turns a strange image into a process. The spiral is not just there, it is being made. Every curve is linked to motion, every loop is connected to time. If we could watch WR-104 for long enough with the right instruments, we would not see a static decoration. We would see the pattern rotate and expand. The pinwheel is not a symbol painted on the sky. It is a machine of winds, orbit, heat, and dust, working slowly from our point of view, but violently by any ordinary standard. The distance adds another layer of strangeness. WR-104 is often described as being around 8,000 light-years away. That means the light reaching us tonight left the system thousands of years before modern telescopes, before electric lights, before the familiar world that lets us sit indoors and casually think about dying stars while perhaps wearing comfortable socks. When we look at WR-104, We are not seeing it as it is at this exact moment. We are seeing an old message, carried across the galaxy at the speed of light. The spiral we study is a delayed report from a distant region of the Milky Way. Astronomy is full of this gentle time travel, and it never quite stops being strange. At the same time, 8,000 light-years is nearby by galactic standards. The Milky Way is more than 100,000 light-years across, so WR104 is not on the far side of the observable universe, or even on the far side of our own galaxy. It is distant from human experience, but still part of our local galactic neighbourhood. This is one of those scale problems astronomy gives us so often. Something can be unimaginably far away and still be relatively close. It is like saying a town is nearby because it is only 3 countries over. Technically, compared with another continent. Perhaps yes. For walking, no. The fact that WR104 belongs to Sagittarius also places it among many other objects that often appear in astronomy discussions. Sagittarius contains star-forming regions, bright nebulae in dense clusters, and the direction of the supermassive black hole at the centre of the Milky Way. It is a region full of activity, not because all of those objects are sitting at the same distance or physically touching one another, but because our line of sight toward the galactic centre gathers many layers of the galaxy together. Looking there is like looking down a long avenue at night, with streetlights, windows, cars and signs all overlapping in the distance. In that crowded view, WR104's spiral is especially remarkable because it is small on the sky. The physical structure may span large distances around the stars, but from Earth, its apparent size is tiny. Resolving it required advanced observing methods, including techniques that push telescopes beyond ordinary imaging. Astronomers used high-resolution observations to separate details that would otherwise blur together. This matters because many objects in space are not limited by how bright they are, but by how small they appear. A lighthouse across a harbour is easy. A firefly across a continent is less cooperative. One of the tools used to study systems like WR104 is aperture masking interferometry, a technique that effectively turns a telescope into a set of smaller paired openings, allowing astronomers to recover very fine detail. That may sound like making a telescope worse in order to make it better, which is exactly the kind of thing science enjoys doing. By carefully controlling how light enters and interferes, researchers can measure structures far smaller than the telescope would normally resolve in a simple image. The result is not just a prettier picture, it is information about shape, size, motion, and orientation. This is why WR104 became so important. It was not merely another dusty Wolf-Rayet system. It became a prototype for a whole class of objects called colliding wind pinwheels. That means astronomers could use it as a clear example of how binary stars with strong winds can create spiral dust structures. A prototype in science is not necessarily the first thing that ever existed. It is often the first thing understood well enough to become a reference point. WR104 gave researchers a pattern they could model, compare, and look for elsewhere. The hidden nature of the pinwheel also reminds us that astronomy often depends on seeing beyond human senses. Our eyes are wonderful, but they are narrow instruments. They detect only a small slice of the electromagnetic spectrum. Space, meanwhile, is glowing, pulsing, absorbing, and reflecting across many kinds of light, from radio waves to gamma rays. A star system can look ordinary in one wavelength and astonishing in another. WR104's dust is warm enough to glow in infrared. So infrared observations reveal the spiral more clearly. It is a little like walking into a dark room with the wrong kind of flashlight, seeing almost nothing, then switching to the right one and realizing the walls were covered in maps all along. Dust itself is part of the hiding and part of the revealing. Interstellar dust can block visible starlight, but the dust made by WR104 is the very material that shows the system's motion. Without dust, the winds might still collide, the stars might still orbit, and the physics might still be dramatic, but we would not get the same bright spiral clue. The dust is both curtain and handwriting. It obscures some things and records others. That is very typical of space. The obstacle and the evidence are often made of the same stuff. To understand why the spiral appears so neat, it helps to imagine the central binary as a rotating source of dust. The stars orbit with a period of about 8 months, or more precisely, observations have measured the pinwheel's orbital rhythm at roughly 241.5 days. During each orbit, fresh dust is carried outward by the flow of stellar wind. Since the dust keeps moving away while the stars continue turning, the pattern stretches into an Archimedean spiral, meaning the spacing of the spiral arms follows a simple relationship with rotation and outward motion. You do not need to hold the mathematics in your head. The simple picture is enough. Turn steadily, flow steadily, and a spiral appears. There is comfort in the steadiness. Around WR104 the conditions are extreme, but the pattern repeats. The stars do not wander randomly around each other. The dust does not spray in every possible direction. The system has a rhythm, and that rhythm has been measured. When astronomers compare images taken at different times, they can see the spiral has moved, consistent with the orbital period. A distant object that looks frozen becomes a clock. Not a neat clock on a bedside table, perhaps, but a dusty astronomical clock turning once every 8 months and leaving its marks in space. The spiral's face-on appearance is part of why WR104 became famous. When something is face-on, we are looking down toward the plane of the spiral, rather than seeing it edge-on. A spiral galaxy seen face-on shows its arms clearly, while the same galaxy seen edge-on might look like a thin streak with a dusty lane. WR104's pinwheel was long interpreted as being nearly face-on to us, which made the shape look especially clean and circular. That view also fed later questions about whether the system's rotation axis might be aimed near Earth. Those questions belong more fully to the later discussion of supernova and gamma-ray bursts, but the root of them starts here, with the way the spiral presents itself in the sky. More recent observations have made the picture more complicated in an interesting way. Measurements of the central stars suggest that their orbit is tilted away from our line of sight more than the spiral's appearance alone once implied. That is not a failure of the old images. It is a reminder that a beautiful pattern can hide a more complex three-dimensional structure. The pinwheel may look simple on the sky, but the actual system has depth, inclination, wind geometry, and dust behavior that researchers are still working to connect. Space rarely gives us a diagram with all the labels already filled in. It gives us a glowing clue and waits to see how carefully we read it. This is one reason WR104 remains scientifically useful. It is not just a solved postcard, it is still a working problem. The broad idea is clear. Massive stars, colliding winds, dust formation, orbital motion, spiral plume. But the details still matter. Where exactly does the dust form? How does it survive near such intense radiation? How does the wind collision shape the plume? How should astronomers reconcile the apparent orientation of the spiral with the newer orbital measurements? These are not questions that make the object less beautiful. They make it better. A mystery that survives better observations is usually a good mystery, and Sagittarius is a fitting hiding place for it. That region of sky already teaches us that beauty and difficulty often come together. The same dust that gives parts of the Milky Way their dark lanes also blocks our view. The same crowded star fields that make the region rich also make it confusing. The same direction that points toward the heart of the galaxy also forces us to look through a great deal of galactic material. WR104 belongs to this setting naturally. It is a bright, rare, massive system, but it is tucked into a complicated view, visible in its full character only when astronomers use the right tools and ask the right questions. For a listener on Earth, there is something calming about that. Not every remarkable thing announces itself loudly. Some of the most interesting structures in the universe are hidden, until we learn how to look. WR104 did not become a pinwheel because humans noticed it. It was already turning, already shedding dust, already writing its spiral into space. Our discovery simply joined the process late. The system had been doing its quiet, violent work for ages before any telescope separated its delicate curl from the surrounding dark. That is a useful thought to carry forward. The pinwheel is hidden, but not absent. It is distant, but not unreachable to understanding. It is complicated, but not beyond explanation. Sagittarius gives it a crowded backdrop. Interstellar dust makes it difficult to see, and the limits of our eyes keep it invisible without special instruments. Yet the spiral is there, and with patience it can be measured. A distant system becomes a pattern becomes a clue becomes a story about two massive stars locked together near the end of their lives. So for now, keep the image simple, a rich section of the Milky Way, a direction full of star clouds and dust. A faint system hidden from ordinary sight. Two massive stars at its centre, circling each other every 8 months. Their winds collide. Dust forms where it almost should not. The dust streams outward and curls into a pinwheel that infrared telescopes can reveal. That is WR104 in its setting, not yet fully explained, but placed on the map of the mind. Once that location is clear, the next question becomes more direct. What kind of star sits at the heart of this system? Before the spiral can really make sense, we have to spend a little time with the kind of star that sits at the heart of it, because WR104 is not built around an ordinary star quietly minding its own hydrogen. It is built around a Wolf-Rayet star, and Wolf-Rayet stars are some of the most extreme, exposed, and restless stars in the galaxy. They are the sort of stars that make our sun look like a calm little reading lamp. A very important reading lamp, of course, and one we are all personally attached to, but still, compared with a Wolf-Rayet star, the sun is steady, mild, and almost shy. A Wolf-Rayet star begins its story as a massive star, not merely a little larger than the sun, not just a bright cousin with a bigger appetite, but a truly massive object born with enough fuel and pressure to live its life in a hurry. Massive stars burn through their nuclear fuel far faster than smaller stars do. That may sound backwards at first. You might expect a star with more fuel to last longer, the way a larger candle might burn longer than a small one, but stars are not candles. A massive star has so much weight pressing down on its core that nuclear fusion runs at an enormous rate. It spends its fuel lavishly, like someone who has just been handed a gift card and absolutely no sense of restraint. Our sun can shine steadily for about 10 billion years in its main lifetime. A very massive star may live only a few million years. That is still an immense span by human standards, longer than civilization, longer than our species, longer than almost any story we can comfortably hold in our heads. But in stellar terms, it is a brief, brilliant existence. Massive stars are born, blaze, change, shed, and die, while smaller stars are still settling into their long middle age. A Wolf-Rayet star is one of the late and dramatic stages in that fast life. What makes it strange is not only its mass, but what has happened to its outer layers. Most familiar stars, including the Sun, keep their inner nuclear furnace hidden beneath layers of hot gas. We see the photosphere, the visible surface, but not the core where fusion truly happens. A Wolf-Rayet star, however, has lost much of its outer hydrogen-rich envelope. The usual outer covering has been stripped away, either by the star's own powerful wind, by interaction with a companion star, or by some combination of both. What remains is hotter, deeper material exposed to space. It is a star that has, in a sense, had its outer clothing torn away by its own intensity. That is why Wolf-Rayet stars look so unusual to astronomers. When scientists study starlight, they split it into a spectrum, a kind of fingerprint made of colours and dark or bright lines. These lines reveal which elements are present and how the gas is moving. Wolf-Rayet stars show strong, broad emission lines from elements like helium, nitrogen, carbon, and oxygen, depending on the specific type. The broadness of those lines tells us that the gas is moving very fast. The chemistry tells us that we are not looking at an ordinary surface composition anymore. We are seeing material that has been processed inside the star and then brought outward or exposed. There are different families of Wolf-Rayet stars. Some show strong nitrogen lines and are called WN stars. Others show strong carbon lines and are called WC stars. A smaller group shows oxygen features and is called WO. These letters are practical labels, but behind them is a story of stellar evolution. A massive star first fuses hydrogen into helium. Later, as its core changes and its outer layers are lost, helium and heavier fusion products become more visible. In the case of WR104, the Wolf-Rayet star is carbon-rich, which matters greatly because carbon is one of the ingredients that can help build dust. That point is easy to pass over too quickly, but it is important. Dust does not come from nothing. To make carbon dust, you need carbon. A carbon-rich Wolf-Rayet wind supplies the raw material. The star has created heavier elements through nuclear fusion and later exposed or expelled them. This means WR104's spiral is not just a pretty shape made around a hot star. It is a visible record of a massive star giving processed material back to space. The carbon in that dust was forged in stellar conditions so intense that ordinary language begins to feel underdressed. A Wolf-Rayet star also loses mass at a tremendous rate. Stars like the Sun have stellar winds too. The solar wind is a stream of charged particles flowing outward from the Sun, and it shapes space weather around Earth. It helps produce auroras when it interacts with our planet's magnetic field, which is a lovely result of something that can also occasionally annoy satellites. But the wind from a Wolf-Rayet star is in another category entirely. It is much stronger, denser, and faster. Material is being driven away from the star at speeds that can reach thousands of kilometers per second. That is not wind in the everyday sense. That is a star actively throwing itself into space. This wind is powered by radiation. Wolf-Rayet stars are intensely luminous. Their light pushes on atoms and ions in the outer layers, especially through countless absorption and emission interactions. In simple terms, the star's own radiation helps shove material outward. It is not a gentle glow sitting politely on the surface. It is pressure. Light may feel weightless to us because we live in a quiet little corner of ordinary experience, but light carries momentum. Around an extremely luminous star, that momentum matters. Enough radiation pushing on enough material can become a wind strong enough to peel a star down and carry its mass away. There is something almost unsettling about that. A star is not just shining, it is eroding itself with its own brightness. It is losing matter because it's so luminous that it cannot hold all of its outer material calmly in place. If the Sun is a lamp, a Wolf-Rayet star is more like a furnace with a door blown open, roaring so strongly that pieces of itself are being carried out into the room. Not a room one should enter, obviously, even with very sturdy slippers. The surface temperature of a Wolf-Rayet star is also extremely high. These stars can be far hotter than the Sun, with surface temperatures reaching tens of thousands of degrees, sometimes much more. Their radiation pours strongly into ultraviolet light, which our eyes cannot see but which has a powerful effect on surrounding gas and dust. This radiation can ionize atoms, break molecular bonds, and make the environment around the star harsh. That is why dust near Wolf-Rayet stars is such an interesting puzzle. Dust grains are delicate compared with the forces around them. They can be heated, blasted, disrupted, or prevented from forming at all. Yet in systems like WR104, dust not only forms, it forms in a structured outflow. The reason it can happen is closely tied to the presence of a companion star. But before bringing that companion fully into view, it helps to understand why a lone Wolf-Rayet star already sets the stage. It supplies carbon-rich material. It produces a fast, dense wind. It creates radiation strong enough to shape the space around it. It is unstable in the broad evolutionary sense, not necessarily changing wildly from minute to minute, but clearly moving through a short and intense late phase of life. A Wolf-Rayet star is not a quiet object waiting for nothing. It is an active transition between massive star life and massive star death. That death can be spectacular. Many Wolf-Rayet stars are thought to be possible predecessors of core collapse supernovae, especially stripped envelope supernovae, where the exploding star has already lost much of its hydrogen and sometimes helium before the final collapse. When the core of such a massive star can no longer support itself, it collapses under gravity. The outer layers are blasted outward, and what remains may become a neutron star or a black hole, depending on the star's mass and structure. The details are complex, and astronomers are still working to connect different types of Wolf-Rayet stars to different kinds of explosions. But the general direction is clear. These stars are near the dangerous end of the massive star road. That is one of the reasons WR104 became famous beyond technical astronomy. A massive Wolf-Rayet star, a beautiful spiral, and the possibility of a future explosion make an irresistible combination. It sounds almost designed for dramatic headlines. But the calm version is more useful. WR104 is important because it lets scientists study how massive, evolved stars lose material before they die. That mass loss matters because it changes the final fate of the star. It affects the type of supernova that may occur, the material blown into space, and the environment into which the explosion eventually expands. In stellar life, what a star loses before death can be just as important as what it keeps. The wind also changes the star's surroundings long before any final explosion. A Wolf-Rayet star carves bubbles, compresses gas, enriches space with heavier elements, and shapes the interstellar medium around it. Its influence can extend far beyond the star itself. A massive star does not live privately. It affects its neighborhood. It blows material into space, stirs nearby gas, and contributes to the chemical evolution of the galaxy. In that sense, Wolf-Rayet stars are both destructive and generous. They tear themselves apart, but in doing so, they return valuable material to the universe. This is where the strangeness becomes more than spectacle. The carbon, nitrogen, oxygen, and other elements associated with evolved massive stars are part of the long chemical story that eventually allows planets and life to exist. The early universe had mostly hydrogen and helium, with only tiny traces of other elements. Heavier elements had to be made in stars and spread by stellar winds and explosions. So when we look at a Wolf-Rayet star-shedding processed material, we are watching one of the ways the universe becomes chemically richer. It is not merely a star losing weight. It is a galaxy being seasoned, which is perhaps not the most formal phrase, but it is difficult to resist. WR104's Wolf-Rayet star is especially relevant because it belongs to the carbon-rich WC class. In this kind of star, the wind carries carbon outward. Carbon is a flexible element, chemically eager and structurally useful. It can form grains under the right conditions. Yet those right conditions are hard to find so close to an intense hot star. This is why the companion becomes essential. The wind from the Wolf-Rayet star collides with the wind from the companion, creating a dense shock region. In that compressed zone, gas can cool and shield itself enough for dust formation to begin. The Wolf-Rayet star provides the carbon-rich ingredients. The binary interaction helps create the workshop. Without that interaction, WR104 might still be an extreme star, but it would not necessarily draw its famous spiral. The spiral exists because the Wolf-Rayet star is strange in the right way, and because it is not alone. Its wind is fast and rich. The companion wind is also strong. Their collision makes a shaped flow. Their orbit turns that shaped flow into a pinwheel. So the Wolf-Rayet nature is not just a label attached to the system. It is the engine of the whole pattern. Another strange feature of Wolf-Rayet stars is how bright they are compared with how small they can be. After losing outer layers, they may be physically more compact than the swollen massive stars they came from, but they remain intensely luminous. This combination, compactness and brilliance, gives them fierce surface conditions. A star that has shed its cooler outer layers exposes hotter regions beneath. The result is a powerful source of radiation and wind, a bare furnace in space. That is why spectra of Wolf-Rayet stars are so distinctive. We are not seeing a normal stellar atmosphere. We are seeing an extended, rushing wind so thick and energetic that the wind itself becomes part of what we observe as the star. That can be a little odd to imagine. With the sun, we usually think of a visible surface, even though the sun is made of gas and does not have a hard ground to stand on. With a Wolf-Rayet star, the wind can be so dense and optically thick that defining the surface becomes less straightforward. What we call the visible star may partly be the outflowing atmosphere. The star is not a neat glowing ball with a thin breeze. It is more like a blazing core wrapped in a storm of its own escaping material. If you tried to draw it simply as a circle with little rays around it, the physics would quietly cough in the background and ask for several more layers. This thick wind is one reason Wolf-Rayet stars were recognized through their spectra, before their nature was fully understood. Charles Wolf and Wolf-Rayet noticed unusual stars in the 19th century whose spectra showed bright emission bands, rather than the more ordinary absorption line patterns seen in many stars. At the time, the physical explanation was not clear. Over the decades, as astrophysics developed, those strange spectra became clues to hot, evolved, massive stars with powerful outflows. That history is a nice reminder that science often begins not with understanding, but with noticing that something refuses to look normal. Wolf-Rayet stars are rare because the phase is short and because only massive stars can enter the classic Wolf-Rayet pathway. A galaxy may contain enormous numbers of ordinary stars, but only a small fraction are massive enough, evolved enough, and exposed enough to be Wolf-Rayet stars at any given time. They are brief fireworks in a galaxy that also contains many long-burning embers. Finding them helps astronomers trace massive star evolution, recent star formation, and the chemical enrichment of galaxies. They may not be common, but they matter far beyond their numbers. Their rarity also gives WR104 extra value. It is not just a Wolf-Rayet star. It is a Wolf-Rayet star in a dust-making binary with a resolvable spiral. That is a very particular arrangement. Many stars are in binaries, and many massive stars have strong winds, but only under certain conditions do colliding winds form dust in a stable, repeating structure that we can observe as a pinwheel. The system is like a natural laboratory that happens to be thousands of light years away and not especially convenient to visit. Still, as laboratories go, it has excellent lighting. When thinking about the Wolf-Rayet star in WR104, it may help to imagine a sequence. First, a massive star is born in a gas cloud. It burns hydrogen rapidly and shines with great intensity. As it evolves, its internal structure changes. Its outer layers become vulnerable to loss through strong winds and possibly through gravitational interaction with a companion. Eventually, the hydrogen-rich envelope is stripped away, and deeper layers rich in helium and later carbon become exposed or expelled. The star becomes a Wolf-Rayet star, hot, luminous, and windy. In WR104, that wind meets the wind of another massive star. Dust forms in the collision zone. The orbit turns the dust stream into a spiral. The strange star at the centre is therefore the first cause in a chain that leads all the way to the pinwheel we see. There is no need to make the Wolf-Rayet star mysterious in a vague way. Its strangeness comes from clear physical facts. It is massive, it is evolved, it is stripped, it is extremely hot, it has a powerful wind, its surface chemistry shows products of nuclear processing, it is likely moving toward a dramatic end. These are understandable ideas, but placed together they create an object very unlike the stars we casually imagine when we look up at night. Most stars in the sky appear as calm points of light. A Wolf-Rayet star reminds us that a point of light can hide a crisis. Even the word star can feel too simple here. A Wolf-Rayet star is not just shining, it is exposing the results of fusion. It is losing mass at a high rate. It is shaping its environment. It is preparing slowly by human standards and quickly by stellar standards for a possible final collapse. It is both an object and a process. That is a helpful way to think about many things in astronomy. The universe is less full of static things than our eyes suggest. Stars are processes, galaxies are processes, nebulae are processes. WR104's spiral is a process made visible. The contrast with the sun is useful but should not make the sun seem boring. The sun is beautifully stable because it is not massive enough to become a Wolf-Rayet star. It does not have the internal pressure or short, furious lifetime of those giants. It will evolve into a red giant much later, shed outer layers, and leave behind a white dwarf, not explode as a core collapse supernova. That quieter future is very convenient for Earth. A Wolf-Rayet star follows a different path because mass changes everything. More mass means stronger gravity, hotter core conditions, faster fusion, greater luminosity, more intense winds, and a shorter life. In stellar evolution, mass is destiny more than almost anything else. This also means Wolf-Rayet stars help astronomers understand the upper end of stellar life. They are clues to what happens when nature builds stars near the massive extreme. How much mass can a star lose before it dies? How does rotation affect its future? How does a binary companion strip or shape it? What kind of supernova will it produce? Will it leave behind a neutron star or black hole? Could some form long gamma-ray bursts under the right conditions? These questions are not all settled, and WR104 sits near several of them. Its beauty is not separate from the research. The spiral is beautiful because it is a visible result of these deeper processes. In a quieter sense, Wolf-Rayet stars are also reminders that stars change identity. A star is not born with one simple label that lasts forever. A massive star may begin as an O-type star, become a supergiant or luminous blue variable, lose mass, become a Wolf-Rayet star, and finally collapse. The labels describe stages, not fixed personalities. WR104's central star is strange because we're seeing it at a late exposed stage, after enormous changes have already occurred. We have arrived in the middle of the story, as astronomers almost always do. By the time a star becomes a Wolf-Rayet star, its earlier life has already shaped what comes next. Its original mass, rotation, metallicity, and binary interactions all matter. Metallicity in astronomy means the abundance of elements heavier than helium. That can affect how efficiently radiation drives stellar winds. In environments with more heavy elements, massive stars may lose mass more easily through line-driven winds. This has consequences for the kinds of Wolf-Rayet stars that form in different galaxies, and for the kinds of supernovae and black holes they may leave behind. A single star's wind becomes part of a much larger galactic pattern. But for WR104, the immediate point remains close and physical. The Wolf-Rayet star is losing a carbon-rich wind. That wind is one half of a collision. The companion provides the other half. The place where the winds meet is not a quiet boundary. It is a shock front, a curved region where supersonic flows slam into each other, heat up, compress, and then stream away. In that region, under the right conditions, dust can condense. The Wolf-Rayet star's strangeness supplies both the violence and the ingredients. The companion helps shape the result. This is why the pinwheel is not merely decoration around the star, it is evidence of the star's nature. If the central Wolf-Rayet star were cooler, calmer, less evolved, less stripped, or less carbon-rich, the system would not behave the same way. If its wind were weaker, the collision would differ. If the chemistry were different, dust formation would be altered. The spiral is a consequence of what the star has become. It is the visible signature of a massive star nearing the end of its life while locked in orbit with another massive star. There is something oddly gentle about understanding that. At first, WR104 may seem like a strange object because of the spiral. Then the spiral leads us inward to the Wolf-Rayet star. The star itself then reveals a deeper kind of strangeness, not visual, but physical. It is a stripped core, a powerful wind source, a carbon supplier, a future supernova candidate, a rare phase of massive stellar evolution. The beauty on the outside is connected to the crisis on the inside, and yet, crisis in astronomy does not always mean panic. It often means transition. A Wolf-Rayet star is not wrong or broken. It is doing what massive stars do when they reach this stage. It is obeying gravity, radiation pressure, nuclear physics, and orbital history. Its wind may look like loss, but that loss feeds the galaxy. Its exposed layers may look violent, but they teach us what stars are made of beneath their surfaces. Its future explosion may sound destructive, but supernovae are among the ways the universe spreads heavy elements. Even the most extreme stars take part in a larger cycle. So when we think of WR104 now, the hidden pinwheel in Sagittarius should no longer feel like a separate ornament floating around an unexplained light. At its centre is a Wolf-Rayet star, a rare and evolved massive star that has already shed much of itself, revealing hotter, chemically changed layers and driving a fierce wind into space. That wind is rich enough, fast enough, and dense enough to matter. It carries the material that will become dust. It collides with the wind of a nearby companion. It helps create the conditions that turn stellar violence into a spiral. The companion is easy to underestimate at first because the famous name WR104 points our attention toward the Wolf-Rayet star, the stripped and powerful object throwing carbon-rich material into space. But the spiral is not made by one star acting alone. At the centre of the pinwheel is a close stellar partnership, two massive stars locked together by gravity, moving around their shared centre of mass with a rhythm that shapes everything we see around them. One star provides the carbon-rich Wolf-Rayet wind. The other, a hot massive companion, brings its own strong wind into the system. The spiral begins where those two winds meet. That is a small sentence for a very large event. Two stellar winds meet. It sounds almost polite, like two neighbours arriving at the same garden fence. In reality, these winds are streams of hot charged gas moving at enormous speeds, driven outward by stars that are far brighter and more violent than the sun. They do not drift together softly. They slam into each other, they compress, they heat, they form a curved shock region between the stars, and from that collision zone, under conditions that are still being studied carefully, dust can begin its strange journey into the surrounding dark. The companion star in WR104 is usually described as a Hotto B-type star, meaning it belongs to the family of massive blue-white stars with high temperatures and strong radiation. It is not as evolutionarily exposed as the Wolf-Rayet star, but it is no quiet bystander. A star like this is luminous, powerful, and young in the broad stellar sense. It gives off intense ultraviolet light and drives its own outflow into space. If the Wolf-Rayet star is the stripped furnace, the companion is another bright engine nearby, and the space between them is not empty. It is a meeting place where pressure, motion, and radiation all argue at once. In an ordinary binary system, two stars may orbit each other for millions or billions of years without producing anything as visually distinctive as a pinwheel. Many binary stars are interesting because of their motion, eclipses, or exchange of material, but WR104 has the special ingredients needed for a spiral dust plume. The stars are close enough that their winds interact strongly. The Wolf-Rayet wind is rich in carbon. The companion wind provides an opposing flow. Their orbit is regular enough that the interaction region rotates around the system in a repeating pattern. Then the newly formed dust flows outward, carrying a record of that motion into space. It helps to picture the two stars not as one circling a fixed other, but as both orbiting a shared balance point. In a binary system, gravity ties the stars together, and the centre of mass lies somewhere between them, depending on their masses. If one star is much heavier, that point sits closer to the heavier star. If their masses are more similar, it lies more between them. Around WR104, the exact details are difficult because the central pair is too close and too bright to resolve easily in ordinary images, but the principle is the same. The two stars are not simply standing in place while dust appears. They are moving continuously, and their movement is the clockwork behind the spiral. The orbital period of this inner pair is about 241.5 days, a little under 8 months. That number is wonderfully useful because it connects the hidden motion of the stars to the visible pattern of the dust. Each time the stars complete an orbit, the dust-forming region has turned once around the system. Meanwhile, dust that formed earlier has been carried farther outward by the stellar winds. The result is a spiral with repeated turns, each part marking material released at a different time. The pinwheel is therefore not just a shape, it is a timeline made of dust. This is one of the clearest ways the companion matters. If the Wolf-Rayet star were alone, its wind might expand outward in a more nearly spherical or irregular way, depending on rotation, magnetic effects, and other details. It might still lose enormous amounts of material, and it might still enrich its surroundings, but it would not naturally draw the same steady spiral. The companion creates the collision surface. The orbit carries that surface around. The outflow stretches it outward. A single star can make a wind, but this pair makes a pattern. A simple kitchen comparison may help, although as usual, the kitchen is not rated for Wolf-Rayet conditions. Imagine holding a hose while slowly turning in a circle. Water sprays outward, and the moving source creates a curved trace on the ground. Now replace the water with dust carried by stellar wind. Replace your calm turning with two massive stars orbiting one another, and replace the garden with a region thousands of light years away in Sagittarius. The comparison becomes less practical, but the basic geometry survives. Rotation plus outward flow produces a spiral. The companion's wind also helps solve a problem that bothered astronomers for decades. Dust around Wolf-Rayet stars should be difficult to make. The radiation is intense. The temperature near the star is high. Small grains should struggle to survive. Yet carbon-rich Wolf-Rayet systems sometimes show warm dust. In WR104, the binary companion provides a way to create a dense, compressed region shielded enough for dust formation to occur. The winds collide, and where they collide, gas is squeezed into a curved interface. Compression increases density. The flow then moves away from the hottest central region. As it expands and cools, dust grains can condense from the carbon-rich material. That does not mean the process is simple. Dust formation near massive stars remains a serious topic of research because the environment is harsh and fast-moving. The gas is not calmly settling like flour in a bowl. It is rushing outward, shocked, heated, cooled, mixed, and exposed to fierce radiation. Tiny grains must begin forming in the middle of all that. It is less like dust gathering on a shelf, and more like trying to knit a scarf in a wind tunnel, while someone points a floodlight at you. Still, nature manages it, because in the right compressed zones, with enough carbon and enough shielding, small grains can begin to grow. The shape of the wind collision region depends on the strengths of the two winds. If one wind is much stronger than the other, it pushes the contact surface closer to the weaker star. If the winds are more evenly matched, the collision zone sits more between them. Around WR104, the Wolf-Rayet wind is powerful, but the companion is massive enough to contribute meaningfully. Their interaction creates a curved shock cone, a kind of wrapped surface that opens away from the star with the weaker wind. As the stars orbit, that cone is dragged into a spiral. The dust forms downstream in that structure and is then carried outward. This shock cone is not a solid wall. it is a region of changing gas conditions. On one side, material from the Wolf-Rayet star rushes in, on the other, material from the companion rushes in. Between them, the flows collide and are deflected. The gas can become turbulent, it can cool in places, it can become dense enough for dust chemistry to proceed. The whole structure rotates with the binary orbit, not because the dust is attached to invisible arms, but because the place where dust forms keeps changing direction as the stars move. The spiral is a trail left behind by a rotating workshop. The companion also affects the system through gravity, though the wind collision is the most visible part of the story. Two massive stars in a close orbit can shape each other's past and future. Massive binaries often exchange material or strip one another over time. In many systems, a companion can help remove the outer layers of a star, making it easier for a massive star to become Wolf-Rayet-like. For WR104 specifically, the present spiral tells us that the companion is close enough and strong enough to interact through winds, but the broader evolutionary history may be more complex. The stars did not simply appear in their current form one morning, fresh and ready to make a pinwheel. They have been influencing each other for a long time. That history matters because massive stars rarely live in isolation. Many are born in groups and pairs. Their lives are shaped by nearby companions, cluster environments, and the clouds from which they formed. A lone star story is sometimes easier to tell, but the universe often prefers partnerships, triples, and crowded family arrangements. WR104 itself is often described as having a wider companion as well, meaning the central dust-making pair may be part of a more complex multiple system. The famous spiral, though, is shaped by the close inner pair, where the Wolf-Rayet star and its hot companion orbit tightly enough for their winds to collide in the right way. The idea of two stars spinning at the centre can be misleading if we imagine them spinning like dancers, with visible ribbons attached. The stars are far too bright and small on the sky for us to watch directly in the casual sense. Astronomers infer their motion through a combination of imaging, spectroscopy, brightness changes, and models. Spectroscopy is especially useful because it measures how light is shifted by motion along our line of sight. When a star moves toward us, its spectral lines shift slightly blueward. When it moves away, they shift redward. In a binary, those shifts can reveal orbital motion even when the stars themselves blur together in an image. This is where newer observations have made WR104 more interesting. For a long time, the dust spiral's nearly circular appearance suggested that we were viewing the system almost face-on. That would mean looking nearly down the axis of the orbit, like looking at a plate from above rather than from the side. But recent spectroscopic work points toward a significantly tilted orbit, possibly around 40 degrees or so from our line of sight, rather than almost perfectly face-on. That creates a puzzle. The dust pattern looks quite face-on, while the stellar orbit appears more inclined. The companion, in other words, is helping astronomers notice that the system may be more three-dimensional than the first beautiful images suggested. This is not bad news for the science. It is the kind of complication that makes the object more valuable. A simple face-on spiral was already remarkable, but a system where the dust geometry and the stellar orbit need careful reconciliation is even more useful. It forces scientists to ask how the dust plume is arranged in 3 dimensions, whether the wind collision structure is tilted or warped, how scattering and dust opacity affect the observed image, and how the wider geometry changes what we think we are seeing. WR104 becomes not only a pretty spiral, but a test of how well we understand colliding winds. The companion star is central to that puzzle, because its orbit determines the rotating collision zone. If the companion's path is tilted, then the shock cone and dust formation region may also have a tilted geometry. But what we observe on the sky is a projection, a flattened view of a 3-dimensional structure. Projection can be deceptive. A tilted ring can look like an ellipse. A spiral viewed at one angle can look clean and circular, while its true shape bends through space differently. Astronomy is full of these perspective problems. We are always looking from one location, our small moving platform called Earth, and the universe rarely provides a second viewing angle for convenience. The companion may also help explain brightness changes in the system. WR104 shows variability, and some of that variation may be connected to dust. As dust forms and moves, it can absorb, scatter, and re-emit light. Depending on the geometry, dust may pass through our line of sight or scatter light toward us. If the orbit is inclined, then the relative positions of the stars and dust structures can produce changing brightness over the orbital cycle. In this way, the companion's motion does not only shape the spiral, it may also help modulate how bright the system appears from Earth. There is a calm lesson in that. When we see a star vary, it is tempting to think only of the star itself changing, brightening and dimming like a lamp with a faulty switch. But in systems like WR104, brightness can change because material moves between us and the light, or because scattering angles change, or because the emission from colliding winds rises and falls with orbital phase. The light we receive is a combined message from stars, winds, dust, geometry, and time. It is not one voice speaking plainly. It is a small choir, and the companion is one of the singers, whether or not we can see it directly. The word companion can sound gentle, almost decorative, but in astrophysics, a companion star can be one of the most important forces in a system. Companions can strip outer layers. They can spin stars up. They can create accretion disks. They can trigger novae, shape planetary nebulae, produce gravitational waves, or help form exotic objects after supernovae. In WR104, the companion's role is not merely to orbit nearby. It makes the difference between a fierce wind flowing outward and a fierce wind being sculpted into a pinwheel. It turns mass loss into geometry. That is why binary systems are so important in modern stellar astronomy. For many years, stars were often explained as if they evolved alone, because isolated models are easier to calculate and understand. Those models are still very useful. But real, massive stars often have companions, and companions can change nearly every part of the story. A star's mass, rotation, surface chemistry, final explosion, and leftover remnant may all depend on whether another star has been close enough to interfere. The universe appears to enjoy interference. It has built a great many stars with partners. With WR104, the partnership is visible in the dust. That makes it unusually accessible. We cannot watch the stars themselves orbit with our eyes, but the spiral gives us an indirect record of their motion. Each turn of the pinwheel is like a groove in a record, preserving the beat of the central binary. If the dust is flowing outward at a roughly steady speed, and if the orbit repeats regularly, the spacing and motion of the spiral reveal the period. The system writes its own dynamics into the surrounding material. Astronomers then read that writing by comparing images across time. This is a lovely reversal of scale. The central orbit is tiny on the sky, too small to resolve easily. The dust plume is larger, spread out over hundreds of astronomical units, and therefore easier to map. The small hidden motion creates the large visible pattern. It is like trying to understand the hand of a clock by watching the shadow it casts across a wall. You may not see the gears directly, but if the shadow moves regularly, you can learn the rhythm of the mechanism. The companion's wind also helps define the opening angle of the dust plume. In models of colliding winds, the shape of the shock region depends on the momentum balance between the two winds. A stronger Wolf-Rayet wind wraps around the companion's wind, and the resulting cone can have a particular width. Dust then forms in or near that outflowing region, so the spiral does not fill space evenly. It follows a confined stream. This is why the early resolved images were so striking. The dust did not appear as a featureless shell. It followed a precise spiral trajectory, showing that the production zone was limited and organized. That confinement is important. If dust formed everywhere around the star at once, the system might look like a broad expanding cloud. Instead, dust forms in a preferred region connected to the wind collision. Then the orbit sweeps that region around. The companion is therefore like the moving arm of a natural drawing tool, not because it physically drags dust with a solid structure, but because its wind defines where the dust can start forming. The star's orbit, the collision zone turns, and the dust trail records the movement. There is a practical way to think about the timing. In one orbit, the dust-forming region completes a full rotation. During that same time, dust already released keeps moving outward. So a fresh arc appears near the centre while older arcs move farther away. Over many orbits, the pinwheel grows outward like a slowly expanding pattern. Eventually the dust disperses into the surrounding interstellar medium. It does not remain a perfect spiral forever. The farther it travels, the more it can be affected by other flows, radiation, and the general environment. The neat inner spiral is the freshest handwriting. Farther out, the message begins to fade into the galaxy. The central stars are also separated by only a few astronomical units, comparable in scale to distances within our own solar system. That is close for two massive, powerful stars. The companion is not drifting lazily at the edge of the system. It is close enough that the wind collision is intense, and the orbital period is measured in months, not centuries. This compact arrangement is one reason the spiral is tight and regular. A wider binary could produce a different pattern, perhaps broader, slower, or harder to detect. The closeness of the pair is part of the pinwheel's character. Even so, nothing about the central region is peaceful. The stars are both hot. Their radiation fields overlap. Their winds collide at supersonic speeds. The shock region may produce excess emission in certain spectral lines. Dust forms downstream and glows in infrared. If you could somehow sit safely nearby, which you absolutely could not, the scene would not feel like a graceful pinwheel. It would be blinding, hot, loud in the language of plasma and radiation, and deeply hostile to anything delicate. The calm spiral we admire from Earth is the distant, cooled, projected result of a violent engine. That contrast is one of the reasons WR-104 works so well as a subject for sleepy science. From far away, the system gives us a smooth curl, an almost gentle form. Up close in thought, it becomes a pair of massive stars fighting gravity, radiation, and their own winds. The companion turns the Wolf-Rayet star's loss into a pattern, but it does so through collision, not kindness. Nature often builds beauty this way. Snowflakes require freezing. Waves require motion. Spiral galaxies require gravity tugging on enormous masses. WR-104 requires two stars pouring themselves into space. As we think about the companion, it is also worth remembering that the stars are not orbiting in a perfectly empty, silent mathematical diagram. They are embedded in their own outflow. The material they lose changes the surroundings into which future material flows. Older dust arcs lie farther out. Newer dust forms closer in. The winds keep pushing through a region partly shaped by previous winds. Over time, the system creates a structured environment around itself. The companion is therefore not only shaping the current spiral. Through repeated orbits, it helps build a layered history around the stars. This layered history may one day matter when the Wolf-Rayet star reaches its final stage. If it explodes as a supernova, the blast wave will not expand into untouched emptiness. It will encounter material the star system has already shed. The density, shape, and composition of that surrounding material can affect the appearance of the explosion and its aftermath. Astronomers study mass loss before supernovae partly because the pre-existing environment can influence what we later observe. UR-104's companion helps shape that environment now, long before any final collapse. That future belongs to a later part of the story, but it is already quietly present in the binary. Massive stars do not live forever. The Wolf-Rayet star is in an advanced stage. The companion, too, is massive and will have its own evolutionary path. Depending on their masses, separation and future changes, the system could go through dramatic transformations. One star may explode before the other. The binary may survive, change orbit, or be disrupted. A compact remnant may remain. The details are uncertain, but the central truth is simple enough. This is not a permanent arrangement. It is a phase. For now, though, the phase is remarkably readable. The two stars circle, their winds collide, the dust forms, the spiral expands. Each part depends on the other parts. Remove the companion, and the dust formation loses its organized collision zone. Remove the Wolf-Rayet star and the carbon-rich wind disappears. Remove the orbit and the spiral loses its rotating source. W104 is not one strange object doing one strange thing. It is a system, and the companion is essential to the system's visible identity. That may be the most useful way to hold it in mind. At the center of the pinwheel are not just stars, but relationships. Gravity relates their motion. Wind pressure relates their outflows. Radiation relates their energy to the surrounding gas. Dust relates their chemistry to the wider galaxy. The companion star helps reveal all of those relationships because it turns the Wolf-Rayet wind into something structured enough for us to study. Without it, WR104 might be another extreme star hidden in Sagittarius. With it, WR104 becomes a spiral clock, a dust factory, and a laboratory for massive binary evolution. So when you picture the pinwheel now, let the center become active. Not a single bright point, but two hot stars turning around each other. One stripped and carbon-rich, pouring out a dense Wolf-Rayet wind. One massive and blue-white, driving its own powerful flow. Between them, a curved shock front forms and rotates. Downstream, in the compressed and cooling material, tiny grains begin to appear. Those grains are caught in the outward rush and carried away from the pair. As the stars continue around their orbit, the next stream forms at a new angle, and then the next, and then the next, until the pattern becomes the elegant spiral that first made WR104 famous. Those two immense outflows are where the pinwheel truly begins, not as a finished shape, not as a neat design already waiting in space, but as a physical process that starts in a narrow, violent region between the stars. The Wolf-Rayet star throws out a fast carbon-rich wind. The hot companion throws out its own wind from the opposite side. The two flows rush away from their stars at speeds that make every familiar idea of weather feel very small, and then they collide. That collision is the drawing point of WR104. It is the place where stellar weather becomes structure. On Earth, wind is something we feel on our face, something that bends trees, pushes clouds, and occasionally steals a hat with unnecessary confidence. Around a massive star, wind means something very different. A stellar wind is a stream of particles driven outward into space by heat, radiation, and pressure. Our sun has one, and even the solar wind can shape the space around planets, trigger auroras, and influence satellites. But the winds around WR104 belong to massive stars, and especially to a Wolf-Rayet star, so they are denser, faster, and far more powerful. They are not a breeze, they are a continuous loss of the star itself. That last idea is worth holding for a moment. The wind is not separate from the star in the way wind on Earth is separate from the ground. The Wolf-Rayet star is actually shedding its own material. Layer by layer, particle by particle, it is sending part of its body into space. This material has been shaped by the star's earlier life and by nuclear processes deep inside it. In WR104, the wind carries carbon-rich matter, which will later matter greatly for dust formation. The companion's wind may be less carbon-rich, but it contributes pressure, motion, and in some models, hydrogen that can help the chemistry along. The pinwheel is born from the meeting of these two streams. The collision is not a simple head-on crash that stops everything in place. The winds are supersonic, meaning they move faster than sound would travel through that gas. When such flows collide, shock fronts form. A shock front is a thin region where gas suddenly changes speed, density, and temperature. You can think of it as the astrophysical version of traffic suddenly bunching up when several lanes narrow into one, though with fewer brake lights and rather more ionized plasma. The gas piles up, heats, and then gets deflected away from the collision zone. The result is a curved surface between the stars, sometimes called a wind collision region. The shape of this region depends on the balance of the two winds. If the Wolf-Rayet wind is stronger, it pushes the boundary closer to the companion. If the companion's wind is stronger, the opposite happens. In WR-104, the Wolf-Rayet wind is extremely powerful, but the companion is also a massive hot star, so the interaction is strong enough to create a stable, repeating structure. The collision surface forms a curved, cone-like shape wrapped around the star with the weaker wind. Then the stars orbit, and that cone does not stay pointed in one direction. It turns with the system. This turning is the key to the pinwheel. A stationary wind collision might produce a bow-shaped shock and a stream of material. A rotating wind collision produces a spiral. As the two stars move around their shared center of mass, the dust-forming region changes direction. Material that formed earlier continues moving outward. New material forms closer in at a slightly different angle. After a while, those outward-moving trails line up into a curling pattern. The result is not a solid arm, not a rigid structure, but a continuous plume of dust that records the orbital motion of the stars. The reason this looks so much like a pinwheel is that the process is steady. The orbit is close to circular, and the dust moves outward at a relatively consistent speed. When a source rotates steadily, while material flows outward steadily, the shape naturally becomes a spiral. This kind of spiral is often described as Archimedean, meaning the spacing between turns is regular if the outflow speed and rotation rate remain stable. You do not need the equation to understand the idea. A turning source makes a trail. The trail expands. Each new part is laid down at a new angle. Over time, a spiral appears. There is something calming about that, because it means the beauty of WR-104 is not accidental in the loose sense. It comes from simple relationships repeated over time. Orbit, flow, collision, cooling, dust, expansion. The system does not need a sculptor. It needs physics doing the same thing again and again. One orbit lays down one winding turn. The next orbit lays down another. The dust already released keeps drifting farther outward, and the central engine keeps producing more. What looks like a delicate cosmic ornament is actually a record of repeated motion. Still, the process is not gentle. Close to the stars, the environment is intensely hostile. The Wolf-Rayet star floods the region with ultraviolet radiation. The companion does the same from its side. Gas is moving at an enormous speed. The shock heats material to high temperatures. At first glance, this seems like one of the worst possible places to make dust. Dust grains are small and fragile. They need atoms or molecules to come together and remain together long enough to grow. Strong radiation can break bonds. High temperatures can prevent condensation. Fast flows can tear structures apart before they settle. It is a little like trying to make frost on the inside of a furnace while the furnace is being shaken. And yet WR-104 makes dust. That is part of why it is so valuable to astronomers. The system shows that under the right conditions, even the harsh surroundings of a Wolf-Rayet binary can become a dust factory. The wind collision compresses the gas, raising its density. Dense gas can cool more efficiently than thin gas. The curved shock region may also provide some shielding from direct radiation, giving grains a better chance to form. As material flows away from the hottest central zone, it cools further. Somewhere along that path, tiny carbon-based grains begin to condense. Those first grains are extremely small. They are not the kind of dust you sweep from a floor, though the word invites that image. Cosmic dust grains can be smaller than smoke particles, built from atoms joining into clusters and then larger solids. Around carbon-rich Wolf-Rayet stars, carbon chemistry plays a major role. Once the earliest stable clusters form, additional atoms can attach to them, letting the grains grow. The details depend on temperature, density, composition, radiation, and the speed of the outflow. This is not a quiet laboratory flask. It is chemistry inside a moving shock structure around two massive stars. Recent models of WR-104 have tried to follow that process more carefully by simulating the wind collision in 3 dimensions and then calculating how dust would glow in infrared light. These models are important because the images alone show the finished pattern, while simulations help test how the pattern could have formed. They can ask where dust begins, how fast it travels, how the winds mix, how instabilities disturb the flow, and whether the companion's hydrogen-rich wind helps the chemistry of carbon dust formation. The answer appears to be that the companion is not just pushing material around. It may also help create the conditions that let dust nucleate at all. The word nucleate simply means that the first tiny seed of a grain forms. That seed then allows more material to gather. It is the beginning step, and it can be the hardest step. In everyday life, you might see a similar idea when water vapor condenses on a cold surface, or when crystals grow from a starting point. In WR-104, dust nucleation happens in a far more extreme setting, but the basic idea is that atoms need a way to assemble into stable clusters. If the gas is too hot or too thin, the clusters fall apart. If it is dense enough and cool enough in the right places, they can survive. Once dust forms, it is carried outward by the flow. This is when the pinwheel becomes visible. The grains absorb light from the hot stars and re-emit that energy in infrared wavelengths. Infrared light is especially useful because warm dust shines there, and because infrared can pass through interstellar dust better than visible light. That is why R104's spiral is not something we simply see with our eyes. It is revealed by instruments that detect the warm glow of dust. The pinwheel is a heat signature shaped by motion. The outflow speed matters because it controls the spacing of the spiral arms. If dust moves outward quickly, each turn spreads farther from the next. If it moves more slowly, the spiral is tighter. The orbital period matters as well. A faster orbit creates more tightly wound patterns for a given outflow speed, while a slower orbit creates wider spacing. In WR-104, the roughly 8-month orbit and the measured dust motion combine to produce the distinctive pattern observed by high-resolution infrared imaging. Astronomers can compare the spacing of the spiral with the orbital rhythm and use that to infer how the dust is moving. This is another reason the pinwheel is more than a picture. It is a measuring tool. The geometry tells us something about the physics. The spiral spacing tells us about outflow speed. The rotation tells us about the orbit. The brightness distribution tells us about dust temperature and density. The fading of the outer parts tells us how the dust expands and cools. A beautiful image becomes a data set, and a data set becomes a way to test models of massive star winds. The system also shows that the dust does not start right at the surface of the stars. Observations and models indicate an inner region where little or no dust is seen, a kind of central cavity before the spiral plume begins. That makes sense because very close to the stars the radiation is too intense, and the gas is too hot for grains to survive easily. Dust formation begins farther out, after the shocked material has travelled enough distance to cool and become suitable for condensation. The spiral therefore does not begin exactly at the stars. It begins after the wind collision has had time to prepare the material. That central dust-free gap is a useful clue. It says the pinwheel is not simply material thrown off already formed as dust. It is gas first, then shocked gas, then cooling flow, then dust. The grains appear after the material has moved away from the most hostile region. This gives the process a sequence, and sequences are helpful when studying systems too distant to visit. First, the stars drive winds, then the winds collide. Then gas is compressed and redirected, then it cools, then grains nucleate and grow, then the dust glows in infrared, then the orbit turns that glowing outflow into a spiral. The spiral is often described as smooth, but at the physical level, the wind collision zone may be full of disturbances. Hydrodynamic instabilities can ripple through the shocked gas. Slight differences in density, cooling, or wind speed can create clumps and uneven structures. Some dust may escape beyond the neat boundaries of the spiral. Some may form more efficiently in one part of the flow than another. The clean image is not false, but it is an ordered view of a messy process. From far away, many small disturbances blend into a graceful plume. That happens often in astronomy. Turbulent details become smooth structures when seen across enough distance. The pinwheel also depends on the fact that the orbit is nearly circular. If the stars moved in a very stretched elliptical orbit, the wind collision and dust production might vary strongly as the stars moved closer and farther apart. That is seen in other systems, such as WR140, where dust formation is more episodic, especially near closest approach. WR104, by contrast, produces a more continuous spiral, because the conditions repeat more steadily through the orbit. That steadiness gives the pinwheel its regular appearance. It is not a one-time puff of dust, it is an ongoing outflow tied to a repeating orbit. This is helpful because it shows that not all dusty Wolf-Rayet binaries make the same shapes. The orbit, separation, wind speeds, chemical composition, and viewing angle all matter. Some systems produce shells, arcs, irregular plumes, or episodic dust clouds. WR104 became famous because its geometry and orientation made the spiral especially clear. It is a prototype, not because every system looks exactly like it, but because it demonstrates the pinwheel mechanism so cleanly. 2 strong winds plus orbit plus dust formation can create a spiral nebula. The viewing angle matters too. If we saw WR104 edge on, the spiral might not look like a neat wheel. It might appear as overlapping arcs, a streak, or a more confusing dusty structure. The face-on or nearly face-on presentation of the plume is why the pinwheel shape stands out. More recent observations suggest the stellar orbit itself may be more tilted than originally thought, which complicates the three-dimensional picture, but the basic point remains. What we see is a projection of a structure in space, and the apparent beauty depends partly on our line of sight. The universe may be doing the same physics from every angle, but only some angles produce a postcard. That thought is oddly comforting. WR104 is not performing for us, but our position lets us see the pattern in a particularly revealing way. If Earth were elsewhere in the galaxy, this same system might look less clear or might not have become famous at all. Astronomy is shaped by perspective in this literal sense. The object is real, the physics is real, but the form we admire depends on where we stand. We are not the centre of the system, we are just in a useful seat. The dust in the pinwheel will not stay in that perfect form forever. As it moves outward, it expands, cools, and becomes more diffuse. Eventually the grains mix into the wider interstellar medium. Some may be destroyed by radiation or shocks. Some may survive long enough to become part of future clouds. Over much longer timescales, dust from stars like this can contribute to the raw material of new stars and planetary systems. That means the pinwheel is not only a sign of what WR104 is doing now, it is part of a larger cycle in which massive stars return processed material to the galaxy. There is a practical humility in that. A pattern we admire for its elegance is also a delivery system for elements. The spiral is beautiful because of its shape, but important because of its material. Carbon dust matters. Dust helps cool gas clouds. Dust shields molecules from radiation. Dust provides surfaces for chemical reactions. Dust becomes part of protoplanetary disks. The grains born in extreme environments can later take part in much quieter ones. The material that begins near a violent Wolf-Rayet binary may someday drift into a cold cloud where stars are forming slowly, silently, and with much less drama. The stellar winds are therefore both destructive and constructive. They strip mass from the stars, collide violently, and carve structures into space. yet they also carry enriched material outward, helping seed the galaxy. WR104 is a reminder that mass loss is not simply a star falling apart. It is a form of exchange. The star gives matter back. The binary shapes that matter. The galaxy receives it. Over millions of years, that exchange becomes part of the chemical story of the Milky Way. When we look at the pinwheel, then, we are seeing several things at once. We are seeing orbit made visible. We are seeing wind pressure made visible. We are seeing dust chemistry made visible. We are seeing time made visible, because each curl marks material that left the central system at a different moment. The spiral is a clock, a weather map, and a chemical trail all layered together. Not bad for something that, from far away, might look like a simple glowing swirl. The process also helps explain why WR104 has been studied across many years. One image can reveal a shape, but repeated images reveal motion. By observing the spiral at different times, astronomers can watch it rotate and expand. The motion confirms that the spiral is linked to the orbital period. It also lets researchers refine the outflow speed and geometry. A static nebula could be interpreted in many ways, but a moving spiral tied to a binary orbit becomes much more specific. The system tells on itself by changing. There is something very human about needing time to understand time-dependent objects. A single glance is not enough. Scientists had to observe WR104 again and again, letting the stars complete more of their orbit, letting the dust move farther, letting the pattern reveal its rhythm. Space is patient because it has no choice. Astronomy has to become patient in response. Sometimes the way to understand a star is simply to keep returning to it, like checking the same quiet window each night until the pattern behind the glass begins to move. By now, the central idea is clear enough to rest in the mind without strain. WR104's pinwheel is made by two massive stars in orbit. Their winds collide and form a rotating shock structure. Carbon-rich material from the Wolf-Rayet star, helped by the dense conditions in the collision zone, forms dust. That dust is carried outward while the stars keep turning. The result is a spiral plume glowing in infrared light. The beauty is not separate from the physics. It is the physics seen from far away. Still, one question naturally remains close behind all this. How can dust exist there at all? The dust is the part of WR104 that almost feels like a mistake at first. Not a mistake in the observations, because the spiral has been seen, measured, modelled, and followed over time, but a mistake in the sense that the environment seems completely wrong for it. Around two massive stars, one of them a stripped Wolf-Rayet star pouring out intense radiation, and a fast carbon-rich wind, you would not naturally expect tiny solid grains to gather together and survive. You would expect the place to be too hot, too bright, too violent, too full of motion. You would expect any delicate particle to be blasted apart before it had time to become anything. And yet, there it is. The warm dust of WR104, glowing in infrared light and tracing a spiral so clear that it became the system's most famous feature. Dust sounds ordinary because we meet it every day. It settles on shelves, hides in corners, and returns with impressive confidence about 6 minutes after cleaning. But cosmic dust is not the same as household dust. It is made of tiny grains of solid material, often carbon-rich or silicate-rich, much smaller than grains of sand, sometimes more like smoke particles in scale. These grains drift between stars, absorb light, scatter light, help molecules form and later become part of new star systems. Dust in space is not just dirt. It is a working ingredient in the galaxy. Without dust, cold clouds would behave differently. Star formation would be changed. Planet formation would lose some of its raw material. Even the chemistry of space would be poorer and less sheltered. In WR104, the dust is especially interesting because it is connected to a carbon-rich Wolf-Rayet star. A carbon-rich Wolf-Rayet star has already moved into a late exposed stage of massive star life. it has lost much of its outer hydrogen layer, revealing deeper material and sending out a powerful wind that carries carbon into space. Carbon is one of the basic materials that can build dust grains. But having carbon is not enough. You also need the right temperature, density, and protection from radiation. That is where WR-104 becomes strange, because the carbon is coming from a star that is also producing a radiation field strong enough to make dust formation difficult. Imagine trying to form tiny soot-like grains near a furnace that is not only hot, but also shining with fierce ultraviolet light and blowing gas outward at thousands of kilometers per second. That is not a calm workshop. It is more like trying to assemble a delicate watch inside a jet engine. The atoms need to meet, stick, and build stable clusters. Those clusters need to survive long enough to grow. If the gas is too hot, the clusters fall apart. If the radiation is too intense, chemical bonds can be broken. If the gas is too thin, atoms do not meet often enough. If the flow is too chaotic, the earliest grains may be disrupted before they become stable. WR-104 manages the process anyway. The key is the place where the winds collide. The Wolf-Rayet star's wind rushes outward in one direction. The companion star's wind pushes back from another. Between them, a curved collision region forms where the gas is compressed and redirected. Compression matters because dust formation needs density. In a thin gas, particles are too widely separated. They can rush through space without meeting the right partners often enough. In a compressed region, atoms and molecules encounter one another more frequently. The gas can also cool more effectively when it becomes dense. So the same collision that sounds violent also creates one of the few places in the system where dust has a chance. That is one of the quiet surprises of astrophysics. A harsh event can create shelter. The wind collision is a shock, and shocks heat gas, which seems bad for dust. But the shock also compresses gas and shapes a flow that can cool as it moves away from the stars. The dust does not need to form right at the blazing surfaces. It can form downstream after the material has been squeezed, redirected, and carried outward far enough that conditions improve. The spiral begins not as dust sitting peacefully beside the stars, but as gas passing through a changing sequence. Fast wind, collision, compression, cooling, chemical clustering, grain growth, and then infrared glow. There is probably a central zone around WR-104 where dust cannot survive well. Too close to the stars, the radiation is too strong and the temperatures are too high. Observations and models of the pinwheel indicate that the dust structure begins at some distance from the central binary, leaving an inner region that is comparatively dust-poor. This is not a minor detail. It tells us that the dust is being made after the gas travels outward, not simply launched as fully formed solid grains from the star. The grains are born in the outflow, not carried whole from the stellar surface like sparks from a fire. Those first dust seeds are called nuclei, and the process of making them is called nucleation. It is one of the hardest steps in dust formation. Once a tiny stable cluster exists, more atoms can attach to it, and the grain can grow. But creating that first stable cluster in a hot moving gas is difficult. Around WR-104, modern simulations suggest that the wind from the companion may be more important than a simple pressure wall. Because the companion is a hot OB-type star with a more hydrogen-rich wind, mixing between the Wolf-Rayet carbon-rich wind and the companion's wind may help the chemistry that starts carbon dust formation. In other words, the companion may not only shape the spiral, it may help the dust begin at the chemical level. That is a lovely bit of complexity. At first, we might imagine one star supplies carbon, the other star simply pushes against it, and dust appears where the pressure rises. That broad picture is useful, but the real system may be more subtle. The companion's wind can change the local chemical mixture. It can influence cooling. It can affect the density and geometry of the shocked flow. It can create conditions where carbon atoms have a better chance of forming stable clusters. The companion is not just the second handle on a cosmic sprinkler. It may be part of the recipe. The dust itself is probably carbonaceous, meaning rich in carbon, rather like very fine cosmic soot. That may sound unromantic, but soot is actually a useful comparison. Carbon dust can absorb ultraviolet and visible light from hot stars and re-emit that energy as infrared radiation. This is why the spiral shines in infrared observations. The dust grains are warmed by the intense radiation of the stars. They then glow at longer wavelengths our eyes cannot see, but infrared instruments can detect. So the pinwheel is not shining like a star shines. It is glowing because dust grains are being heated. This heating and cooling gives astronomers information. Dust close to the stars is hotter and brighter in certain infrared wavelengths. Dust farther out is cooler and fainter. By measuring the infrared emission, scientists can estimate dust temperature, grain properties, and how the material is distributed. Models of WR104 have used radiative transfer, which is a way of calculating how light moves through and interacts with matter to reproduce the observed spiral and its energy output. These models suggest small grains in the inner part of the nebula, with possibilities for larger grains farther away. Grain size matters because it changes how dust absorbs and emits light. Tiny grains do not behave exactly like larger grains. A useful comparison is a stone and a speck of ash in sunlight. Both can be warmed by light, but they respond differently because of size, composition, and surface area. In space, dust grains are so small that their temperatures and emission patterns are strongly shaped by their size. By studying the infrared glow of WR104's dust, astronomers are not merely admiring the spiral, they are testing what the grains are made of and how big they might be. The pinwheel becomes a kind of remote dust laboratory, with the central stars providing the heating and the dust itself providing the signal. The amount of dust is also important. WR104 and systems like it are part of a larger discussion about where cosmic dust comes from, especially in galaxies and environments where dust appears to have formed quickly. Massive stars live fast, so they can contribute enriched material early in a galaxy's history. Carbon-rich Wolf-Rayet binaries may be significant dust producers under the right conditions. They are not the only source of cosmic dust, and the full cosmic dust budget is a large and active subject. But WR104 shows that colliding when massive binaries can produce dust efficiently even in hostile conditions. That makes it more than a local curiosity. It is a clue to galactic chemical recycling. The dust creation rate estimated for WR104 is not huge compared with the total mass of a star, but it is meaningful because dust grains are tiny and because the process repeats. The system has been forming dust over many orbits. Each orbit lays down another turn of the spiral. Each turn carries material outward. Over time, the grains disperse into the surrounding space. The pinwheel is therefore a temporary structure, but the dust may continue onward, mixing into the interstellar medium. It may be altered, damaged, or destroyed in later shocks, but some fraction may survive and become part of future clouds. That journey is easy to miss because the spiral is so visually satisfying that we may think of it as the finished object. But the spiral is a stage. Dust forms near the binary, glows as it is warmed, moves outward, cools, fades, and eventually blends into the galaxy. It does not remain a perfect pinwheel forever. The neat inner turns are the freshest and clearest. Farther away, the material thins and becomes harder to trace. The dust that begins as part of a famous spiral may end as ordinary interstellar material, drifting among many other grains. The showy beginning becomes quiet background. There is something very concrete and useful about that. Dust is one of the ways stars connect to future stars. A massive star manufactures heavier elements, loses some of them through winds, and later may explode. Those materials spread through space. In cold clouds, dust helps shield molecules from radiation and allows chemistry to happen on grain surfaces. In disks around young stars, dust grains can collide, stick, grow, and begin the long path toward planetesimals and planets. A grain forming in WR104 is not a planet, of course. It is much too small and much too close to violence, but chemically and physically, it belongs to the same broad story of solid matter in the universe. The phrase, dust that should not exist, is useful as a starting point, but it needs care. The dust does exist, so the real meaning is that our first simple expectation fails. If we imagine only an isolated hot Wolf-Rayet star, dust formation seems unlikely. Once we include the companion, the colliding winds, the dense shock region, cooling flows, chemical mixing and orbital geometry, the impossible becomes possible. This is often how science works. Nature does something that seems unreasonable. Then instead of deciding nature is wrong, we improve the picture until the unreasonable thing becomes understandable. WR104 is a good example, because the visible spiral forced astronomers to take the dust seriously. Dust shells around Wolf-Rayet stars had long been puzzling, because the intense radiation should make dust survival hard. The resolved pinwheel showed that a binary companion and interacting winds could explain the creation of a confined dust stream. That was a major shift from simply knowing dust was present to understanding how the geometry and motion made it. A blurry infrared excess can tell you dust exists. A resolved spiral can tell you how dust is being produced and carried away. The dust stream is confined because the grains form in a specific region connected to the wind collision, not everywhere around the star equally. This is why the spiral arms are distinct. If dust formed uniformly in all directions, WR104 might be surrounded by a shell or a broad cloud. Instead, the dust forms in the rotating collision zone, so it traces a narrow outflow. The stars orbit, the formation region turns, and the dust draws the spiral. The confinement is the evidence of the mechanism. It says the dust is not random, it is tied to the binary interaction. Hydrodynamic instabilities may complicate this neat picture. The shocked winds are not perfectly smooth. Fast, dense flows can ripple, clump, and mix. Some dust may escape beyond the clean boundaries of the spiral. Some parts of the flow may be denser or better shielded than others. Simulations suggest that the wind collision zone can produce structures that are more complex than a simple textbook cone. This does not erase the pinwheel. It enriches it. The spiral is the large-scale order, while instabilities provide smaller-scale texture and variation. The universe is rarely perfectly tidy, even when it draws something tidy-looking. The dust also affects how WR104 appears over time. As dust forms and moves, it can change the system's brightness, especially in infrared. It may also cause dimming or variability in visible light if dust passes through or near our line of sight. Recent work has explored whether dust-related eclipses or obscuration events can help constrain the system's geometry. That makes sense because dust is not only glowing material, it can also block and scatter light. Depending on where it is relative to the stars and Earth, it can hide parts of the system or redirect light toward us. Dust is both lamp and curtain. This dual role makes interpretation tricky. If WR104 brightens in infrared, is that more dust, hotter dust, a change in viewing angle, or a change in the collision region? If visible light dims, is dust crossing the line of sight, or is something else happening in the stars or winds? Astronomers answer these questions by combining different kinds of observations: images, spectra, light curves, and models. One data type alone can mislead. Together they build a more reliable picture. This is especially important for a system where the central stars are hidden inside bright winds and dust. The dust grains themselves do not care that they are scientifically inconvenient. They form where the local conditions allow them to form, and then they move outward. That is a good reminder that nature is local. We may describe WR104 as an extreme environment overall, but dust formation depends on the exact conditions in a particular region of the flow at a particular time. The whole neighbourhood may be hostile, but one compressed cooling pocket can be suitable. It is like saying a desert is dry, while still recognizing that a small shaded crack may hold moisture. The broad description is true, but the local detail decides what happens. In WR104, the local detail is created by the binary. The companion's wind collides with the Wolf-Rayet wind. The shock compresses the gas. The flow carries material away. Cooling and chemical mixing create a path toward grain formation. Radiation heats the grains once they exist, making them visible in infrared. Orbital motion organizes the whole process into a spiral. Each piece is necessary. The dust is not an afterthought sprinkled around the stars. It is the product of the system's structure. There is a small irony here. The same stars that threaten dust survival also make the dust visible. Without the intense radiation, the grains would not glow so brightly in infrared. Without the powerful winds, the gas would not be compressed and shaped. Without the harsh Wolf-Rayet stage, there would not be such a carbon-rich outflow. WR104 makes dust not despite being extreme in every way, but partly because its extremes combine in a useful order. Too much radiation alone would destroy. Wind collision alone without carbon would not make the same grains. Carbon without compression might not condense. But together in this particular binary, they produce the pinwheel. This is why WR104 can feel almost like a contradiction that resolves itself as we examine it. A hot star should be bad for dust. A wind collision should be violent. A massive binary should be chaotic. Yet the collision creates density. The carbon supplies material, the orbit provides regularity, and the radiation lets the grains glow where we can detect them. The contradiction becomes a process. The process becomes a pattern. The pattern becomes a way to understand massive stars. As the dust flows outward, it records not only the present motion of the stars, but also the recent history of the system. Inner dust is younger, outer dust is older. The spacing between spiral turns corresponds to the orbital rhythm and the outward speed. The brightness of each part depends on temperature, density, and grain properties. If dust production changes, the spiral may show that as variations in brightness or thickness. In this sense, the dust plume is a memory. It holds information from past orbits and lets astronomers read the binary's behavior across time. That is one reason repeated observation is so valuable. A single image shows where the dust is. A series of images shows how it moves. Infrared monitoring can show whether dust production is steady or variable. Spectroscopy can show how the stars move and how their winds behave. Models can test whether the observed spiral can be produced by a particular dust formation radius, grain size, wind speed, and viewing angle. WR104 is not understood by one measurement, but by fitting many measurements into one physical story. The story still has open questions. Exactly where does dust nucleation begin? How much mixing between the two winds is needed? How do instabilities affect the spiral edges? How does the newer orbital inclination measurement fit with the face-on appearance of the dust plume? How much dust escapes the immediate spiral and blends into the wider environment? These questions are not signs of failure. They are signs that WR104 is a real system, not a simplified diagram. Real systems always keep some details for later. For a calm listener, perhaps the most useful thing to remember is this. The dust around WR104 is delicate, but it is not helpless. It forms in the one place where the system gives it a chance. It begins in compressed gas shaped by colliding winds. It grows as the flow moves outward and cools. It survives long enough to glow in infrared light. It traces the orbit of two stars we cannot see directly as separate points. It turns violent stellar weather into a visible spiral. The dust should not exist only if we imagine the environment too simply. Once we include the full binary system, its existence becomes one of the most interesting clues WR104 offers, and there is something quietly satisfying in that. A tiny grain of carbon dust near WR104 is small enough to seem unimportant. It has no dramatic name, no bright surface, no familiar shape. Yet billions upon billions of such grains create the pinwheel. They reveal the orbit, they expose the wind collision. They let us study a massive star near the end of its life. They may eventually drift away and become part of the ordinary dust of the Milky Way. The small thing carries the large story, so the next time the spiral rests in your imagination, it may help to see it not as a single glowing ribbon, but as a stream of tiny grains, each one formed under difficult conditions, each one warmed by fierce starlight, each one moving outward from the central pair. Together they make the pinwheel visible. Together they turn hidden physics into a shape. Watching WR104 change is one of the reasons this system feels so different from many distant stars. Most stars, even very dramatic ones, appear fixed to us across a human evening. They may be burning, swelling, pulsing, losing mass, or racing through space, but from Earth they usually sit there as points of light, giving away their secrets only through careful measurements. WR104 is different because its dust spiral can be followed as it turns. Not quickly, not in the way a wheel turns on a bicycle, and certainly not in the way a sleepy person turns over after realizing one side of the pillow has become mysteriously warm. But over months and years the pinwheel changes, and those changes let astronomers connect the visible spiral to the hidden motion of the stars at its centre. This is where the dust becomes a clock again. Each fresh stream of dust is formed near the central binary, carried outward by the wind flow, and left behind as the stars continue their orbit. The central pair completes an orbit in about 8 months, and the spiral rotates with the same rhythm. From our point of view, that means the pattern does not simply sit in space like a painted sign. It advances, it turns, it expands. Observations taken at different times show the dust plume in different orientations, and when those images are placed in sequence, the pinwheel seems to rotate in the plane of the sky. There is something deeply satisfying about that, because it turns a distant object into a moving system we can understand. Astronomy often deals with things that change too slowly for us to watch directly. Galaxies evolve over hundreds of millions of years, nebulae spread over thousands. Stars spend most of their lives so gradually that a single human lifetime is barely a blink in their story. But WR104 offers a rare exception. The stars at its centre orbit quickly enough, and the dust glows clearly enough, that the motion can be tracked across years of observation. It is still slow by ordinary standards, but fast enough for science to catch it in the act. The first resolved images of the spiral were astonishing because they showed a pattern on scales that had been hidden before. Instead of a vague dusty glow, astronomers saw a confined plume following a spiral path. Later observations across many epochs made the picture stronger. The spiral was not a random shape. It rotated in a way tied to the binary orbit. The dust flowed outward while the central engine continued turning, and the whole structure behaved like the visible output of a hidden machine. For a system thousands of light years away, that is an impressive confession. To see the spiral at all, astronomers had to use high-resolution infrared techniques. The dust around WR104 shines most clearly in infrared light, because the grains are warm. Visible light from the central stars is difficult to interpret through dust and distance, but infrared observations reveal the thermal glow of the dust plume. Even then, the apparent size of the structure on the sky is tiny. Resolving the spiral required clever methods, including aperture masking on large telescopes, which can recover details far finer than ordinary imaging. It is one of those scientific methods that sounds almost backwards at first, because astronomers deliberately place a mask over a large telescope to make it act like a small interferometer. This is a little like putting your hand over part of a flashlight and somehow seeing better, which is not recommended for household astronomy, but in the controlled world of optics, it can work beautifully. The result was not just a more detailed image, it was a way to measure motion. By comparing the spiral across time, researchers could estimate the period of the system and the outward speed of the dust. The pattern behaved as though the dust plume was being laid down by a rotating binary, with one complete turn linked to one orbit. The measured period settled around 241.5 days, a remarkably specific number for something hidden in Sagittarius. Once that period was known, WR104 became not just a pinwheel in appearance, but a timed pinwheel, a stellar system whose dusty arms mark the rhythm of two massive stars circling each other. The human mind enjoys this kind of pattern. We like seeing motion become form. A record groove preserves sound, tree rings preserve seasons, ripples preserve the fall of a stone into water. WR104's spiral preserves orbital motion. The central stars are too close together for us to separate directly in those early images, but the dust plume spreads the information outward where we can study it. In a sense, the stars write too small for us to read, so the dust rewrites the message in larger letters. The viewing angle made the image even more striking. The spiral appeared almost face-on, meaning we seemed to be looking down onto the pinwheel rather than across its edge. This is why the spiral looks so clean and circular. If you look at a plate from above, you see its round shape. If you look at it from the side, you see a thin line. WR104's dust plume looked like the plate from above, and that led to the early idea that the central binary orbit might also be almost face-on to us. At first, that seemed like a reasonable assumption. If the dust spiral lies in the orbital plane of the binary, and the spiral looks face-on, then perhaps the orbit is face-on too. That would mean the rotation axis of the system, the direction perpendicular to the orbital plane, might point close to Earth. For studying the spiral, this was convenient. A face-on view made the pinwheel beautiful and easier to interpret. But for the future fate of the Wolf-Rayet star, it raised a much more dramatic question. Massive Wolf-Rayet stars are expected to end their lives violently, often as supernovae. In some circumstances, a very massive, rapidly rotating strip star may produce a long gamma-ray burst when it collapses. A gamma-ray burst is a narrow beam of extremely energetic radiation, one of the most powerful kinds of explosions in the universe. These bursts are not like ordinary starlight spreading softly in every direction. They can be strongly beamed along the rotational poles of the collapsing system. So if a future explosion sends a gamma-ray burst in a direction pointed away from us, Earth is not in the beam. If it were pointed directly toward us from close enough within our galaxy, that would be a far more serious matter. This is how WR104 acquired its alarming nickname. Because the dust spiral looked nearly face-on, some people wondered whether the star's rotational axis might be pointing toward Earth. If the Wolf-Rayet star eventually collapsed and produced a gamma-ray burst along that axis, could Earth be in the path? The idea was dramatic, easy to explain, and not exactly soothing. A beautiful spiral that might be aimed at us sounds like something from science fiction, and so WR104 was sometimes called a Death Star. The nickname was memorable, although perhaps a bit unfair to the star, which has not, to our knowledge, built a space station, worn a black cape, or threatened any small moons. Still, the concern was not invented from nothing. It came from a chain of reasoning. WR104 contains a massive Wolf-Rayet star. Such stars may become supernovae. Some stripped massive stars may be connected to gamma-ray bursts under certain conditions. The dust spiral looked face-on. A face-on view might mean the polar axis was near our line of sight. A gamma-ray burst, if produced along that axis, could be directed toward Earth. Each step had some scientific basis, but each step also had uncertainty. The problem was that popular headlines tend to compress uncertainty into drama. Complex system with several unresolved geometric and evolutionary questions is a less clickable phrase than Death Star, although probably better for everyone's blood pressure. The calmer view is that many things would have to line up. The Wolf-Rayet star would have to produce the right kind of explosion. Not every Wolf-Rayet star makes a gamma-ray burst. It would likely need the right mass, rotation, magnetic conditions, and internal structure at collapse. The beam, if one formed, would have to be pointed toward us. The distance and energy would matter. The atmosphere's response would matter. the timing is also not human. The star may explode in the future, but the future in stellar evolution can mean thousands to hundreds of thousands of years. This is not a scheduled event waiting for Tuesday afternoon, which is good, because Tuesday has enough responsibilities already. For years, scientists treated the WR-104 question with caution. The early pinwheel images suggested a very low inclination, meaning a near face-on view. That did not prove danger, but it made the geometry interesting. Other scientists pointed out that the gamma-ray burst scenario required several assumptions and that the actual risk was likely low. It became one of those astronomical stories where the object itself was scientifically rich, but the public reputation focused on the scariest possible interpretation. WR-104 was a dust-making binary, a prototype colliding wind pinwheel, a rare laboratory for massive star physics, and somehow also the Death Star in headlines. The poor thing was doing actual astrophysics and got cast as a villain. Their newer spectroscopy added an important twist. By observing the light from the stars over many years and measuring how spectral lines shifted, astronomers could estimate the orbital motion of the central pair more directly. Spectroscopy gives access to radial velocity, the motion toward and away from us. A perfectly face-on binary would show very little radial velocity from orbital motion, because the stars would mostly move across our line of sight rather than toward and away from us. But the observed velocity curves indicated that the orbit is not nearly as face-on as the dust spiral seemed to suggest. The orbit appears significantly inclined, perhaps around 45 degrees, with lower values around the mid-30s still possible. That result brought relief and confusion at the same time. Relief, because if the stellar orbit and likely polar direction are tilted well away from us, then the simple aimed directly at Earth. Fear becomes much less plausible. Confusion, because the dust spiral still looks very face-on in images. That means the geometry of WR-104 is more complicated than the early picture. The orbit and the apparent dust plume orientation do not match as simply as expected. For anxious headline readers, the update is calming. For astronomers, it is exciting in the way a difficult puzzle is exciting. The system is safer in one sense, but more interesting in another. This is a good example of how science changes the emotional shape of a story. At first, WR-104 looked like a neat spiral pointed toward us, with a possible future explosion. Then the story became more careful. Yes, it is a massive Wolf-Rayet binary. Yes, it may eventually explode. Yes, gamma-ray bursts are real. But no, we do not know that WR-104 will produce one, and newer measurements suggest the orbit is tilted away from the direct line of sight. So the best current picture is not a Death Star aimed at Earth. It is a complex colliding wind binary whose dust spiral still needs better three-dimensional modelling. Again, not as dramatic on a movie poster, but far more useful. The phrase, "watching the spiral turn," matters here because the same visual evidence that made WR-104 famous also created the original worry. The pinwheel looked face-on because its motion appeared to happen in the plane of the sky. Imagine watching someone swing a garden hose overhead while water sprays outward. If you are looking from above, the spray makes a circular pattern around the person. If you see that pattern as a circle, you may assume you are looking down the axis of rotation. WR-104's early dust images looked similar. That was the garden hose analogy, often used to explain why the system seemed possibly aligned with Earth. But the universe does not always match our simplest analogy. A dust plume is not a rigid disk. It is a three-dimensional flow shaped by colliding winds, cooling, dust formation, radiation, and viewing angle. The dust may not lie exactly in the same plane as the stellar orbit, or the observed brightness may emphasize parts of the plume that make it look more face-on than the orbit truly is. Projection effects can hide depth. Dust opacity can hide some parts and highlight others. The shock cone may have a broad opening angle. The structure may graze our line of sight in some phases. The result is that a clean-looking spiral can still come from a more tilted central system. That is not a weakness of astronomy. It is part of the job. Every observation of a distant object is a projection of a three-dimensional reality onto the flat sky. Scientists must work backward from light, spectra, timing, and models. They build a picture, test it, and then revise it when better evidence appears. WR-104's Death Star reputation came from an earlier interpretation of its geometry. The newer spectroscopy does not erase the pinwheel. It improves the story by showing that the central orbit is probably tilted. The object did not change, our view of it did. There is also a lesson here about risk. Space is full of dramatic possibilities, but possibility is not the same as probability. A nearby gamma-ray burst pointed at Earth would be serious, but the chain connecting WR-104 to that scenario is long. The star must explode in a particular way, at an unknown future time, with a beam formed and aligned toward us. The newer orbital measurements make that alignment less likely. That means WR-104 is not something to fear while falling asleep. It is something to understand. The universe has plenty of real hazards, but it also has a habit of sounding more dangerous when described without scale, probability and uncertainty. If anything, WR-104 is a reminder that beauty can be misunderstood when we rush. The pinwheel looked like a target, and the human brain is very good at turning target-like things into stories about being targeted. But the spiral is not aimed with intention. It is not watching Earth. It is not choosing a direction. It is a wind-carved dust plume shaped by orbital motion and seen from one particular angle. The stars at its centre are not villains. They are massive objects obeying physics. If they someday explode, that event will be part of stellar evolution, not a personal message from Sagittarius. The slow turning of the spiral is still wonderful. Over time, images show the dust rotating and expanding, and that motion confirms the binary nature of the system. It lets astronomers trace the orbit indirectly. It helps measure the outflow speed. It reveals that dust formation is persistent rather than a one-time event. It shows that colliding winds can create a repeating, organised structure. The same spiral that once made people uneasy also provides the data that helps reduce the worry. That is a neat little reversal. The thing that looked threatening became the thing scientists used to understand the system more clearly. There is something almost comforting in that scientific patience. The first images astonished astronomers. The early models explained the pinwheel. The longer monitoring refined the period and dust motion. The spectroscopy later challenged the face-on assumption. Each stage made the story less like a dramatic headline and more like a real object. Real objects are usually more complicated than headlines, and much more interesting. WR-104 is not less fascinating because it is probably not aimed at us. It is more fascinating because the dust spiral and stellar orbit appear to disagree in a way that demands better physics. For the listener, the safest way to hold the Death Star nickname is as a historical footnote, not a conclusion. It tells us how WR-104 entered public imagination. It tells us how a face-on pinwheel, a massive Wolf-Rayet star, and the possibility of gamma-ray bursts combined into a memorable scare. But it does not define the system. The better name remains the pinwheel star because that name points to what we actually observe: dust turning through space, shaped by two massive stars and their colliding winds. And even pinwheel star is a simplification. WR-104 is not one star, not one wheel, not one simple flat spiral. It is a multiple system with a close Wolf-Rayet and OB pair, a wider companion, powerful winds, dust chemistry, infrared emission, orbital motion, possible obscuration events, and a geometry that still asks for more study. The nickname gives us a handle, but the science asks us to open the door and look inside. So picture the spiral turning again, not as a weapon, not as a warning sign, but as a moving record. Fresh dust forms near the wind collision zone. Older dust travels outward. The pattern rotates with the orbit. From Earth, telescopes collect infrared light that left the system thousands of years ago. Astronomers compare one observation with another and slowly reconstruct the motion. A system once given a frightening nickname becomes a patient lesson in perspective, probability, and the difference between looking aimed and being aimed. By the time a star becomes something like the Wolf-Rayet star in WR-104, it has already lived through the easy part of its life. If anything about being a massive star can really be called easy. It has burned fiercely, spent fuel quickly, lost layers into space, and revealed parts of itself that most stars keep hidden until much later, or never reveal in quite the same way at all. It is not a young, calm star settling into a long routine. It is a star in an advanced state, stripped, hot, bright, and restless, with a powerful wind carrying its own material outward into the galaxy. That is why the question of a supernova naturally follows WR-104 wherever it goes. A Wolf-Rayet star is not expected to shine gently forever. Massive stars do not usually get quiet endings. They do not fade like a lamp being turned down. When the core of a massive star reaches the point where it can no longer support itself against gravity, the collapse can be sudden and catastrophic. The outer layers, or what remains of them, can be blasted outward in a supernova, while the core may become a neutron star or a black hole. In that sense, WR-104 is not only a beautiful pinwheel, it is also a system with a future. The important thing is not to rush that future. Astronomy deals in timescales that do not fit neatly into human worry. WR-104 may be close to the end of its life, compared with a star like the Sun, but close in stellar evolution can still mean thousands of years, tens of thousands of years or more. We do not have a date. There is no calendar entry, no cosmic appointment reminder, no little note from Sagittarius saying, "Supernova at 9:30, please bring snacks." The star is in a late phase, but late for a massive star is not the same as imminent for us. Still, the broad direction is clear. The Wolf-Rayet star in WR-104 has already lost much of its outer, hydrogen-rich envelope. That matters because supernovae are partly classified by what material appears in their spectra when they explode. A star that still has a thick hydrogen envelope may produce one kind of core collapse supernova. A stripped star, one that has lost hydrogen and perhaps much of its helium, can produce a different kind, often called a stripped envelope supernova. These are the supernovae known as Type 1b or Type YC, depending on the details of what elements are visible. A carbon-rich Wolf-Rayet star, especially one in the WC class, is often discussed in connection with Type 1c supernovae because it has lost so much of the outer material that would otherwise show hydrogen or helium. That classification may sound technical, but the idea is simple enough. When a star dies, the explosion carries a chemical signature. If hydrogen is present, we see it. If hydrogen is missing, that tells us something about what happened before the explosion. In WR-104, the powerful wind and possible binary history have already removed outer layers, so any future supernova would not be the same as the explosion of a red supergiant still wrapped in a huge hydrogen envelope. WR-104 has already been undressed by stellar evolution, which is not a phrase one should use too loudly at an astronomy conference, but it is reasonably accurate. The final collapse begins deep inside the star, far below the wind's dust and visible spiral. A massive star spends its life fusing lighter elements into heavier ones in its core. Hydrogen becomes helium. Later, helium can become carbon and oxygen. In the most massive stars, fusion continues through stages, building heavier elements in shells around the core. This process can continue until iron group elements form. Iron is a problem for a star because fusing iron does not release useful energy in the same way. Once the core is dominated by iron and no longer producing enough outward pressure from fusion, gravity wins. The core collapses in a fraction of a second. It is a frighteningly fast event after such a long preparation. Millions of years of stellar life lead to a collapse that unfolds almost instantly. The core compresses to extraordinary density. The outer layers fall inward, rebound, and interact with a flood of neutrinos and shockwaves. The details of how the explosion succeeds are still an active area of research, because massive star death is complicated, and the universe does not always make its equations bedtime-friendly. But the visible result can be a supernova, a temporary brightening so powerful that one star can rival the light of a whole galaxy for a time. If WR104 eventually explodes, the event would be dramatic from an astrophysical point of view, but because it is thousands of light years away, it would not look like a second sun in the sky. Depending on how much dust lies between us and the system, how bright the explosion is, and how the light travels through the crowded direction of Sagittarius, it might become visible with instruments, perhaps even noticeable in certain wavelengths. But we should be careful not to imagine the night suddenly turning into daylight. Interstellar dust in the plane of the Milky Way dims visible light, and WR104 is not sitting next door. Space has distance, and distance is very good at reducing drama before it reaches us. The dust around WR104 would also play a role in the future explosion. The star has not been living in a clean, empty bubble. It has spent a long time losing material through its wind. The binary has shaped that material into a spiral. Older dust and gas have been carried outward. If a supernova blast eventually expands from the Wolf-Rayet star, it will run into the material that the system has already placed around itself. That surrounding material is called circumstellar material, which simply means matter around the star. It can affect how the supernova looks, how the shockwave evolves, and what kinds of radiation are produced as the explosion slams into the older wind. That is a useful reminder that a supernova is not only about the star at the moment it dies. It is also about the star's whole previous life. The wind history matters, the mass loss matters, the companion matters, the dust spiral matters. A massive star prepares the stage for its own ending by shedding material long before the final collapse. When the explosion comes, it does not enter a blank universe. It enters a space already shaped by the star's past behaviour. WR104 is, in a sense, writing the environment into which its own final blast may someday expand. The companion star makes the future more complicated. In a single star model, we can imagine one massive star evolving, collapsing, and leaving a remnant. In a binary system, the companion can change the story before, during, and after the explosion. It may have helped strip the Wolf-Rayet star earlier in life. Its gravity affects the orbit. Its wind shapes the surrounding material. If the Wolf-Rayet star explodes, the companion may survive, but its orbit could be altered. If enough mass is lost suddenly, the system could be disrupted. The surviving star might be flung away as a runaway star, carrying the memory of the explosion in its motion. Or the binary might remain bound with a new compact object in place of the Wolf-Rayet star. Both possibilities are fascinating. A surviving companion racing through space would be like a witness leaving the scene at high speed. A bound system with a neutron star or black hole would become a different kind of binary altogether. Later, the companion itself would continue evolving, because it too is massive. Over very long times, the system could pass through another dramatic stage. Massive binaries are not simple stories with one ending. They are branching histories shaped by mass, timing, gravity, and explosions. The remnant left by the Wolf-Rayet star depends on the mass of the core and how much material falls back after the explosion. If the core is not too massive, it may become a neutron star, an object so dense that a spoonful would weigh unimaginably much, which is one of those phrases astronomy uses when it wants to make spoons feel important. If the core is heavier, or if much of the exploded material falls back inward, the result may be a black hole. For many Wolf-Rayet stars, a black hole is a serious possibility. But for any specific star, the final outcome depends on details that are difficult to know from far away. This uncertainty should not feel disappointing. It is honest. Stars are not perfectly labelled fireworks. Astronomers can identify the stage, estimate the mass, study the wind, model the orbit, and infer future possibilities, but they cannot say exactly what WR104 will leave behind without knowing its deepest internal structure. The surface and wind tell part of the story. The core holds the rest, and the core is hidden, not just behind dust, but behind the star's own physics. There is also the question of whether WR104 is rotating rapidly enough to produce something more extreme than an ordinary stripped envelope supernova. Long gamma-ray bursts are thought to be connected to the collapse of some massive, stripped, rapidly rotating stars. In these cases, a newly forming black hole or compact engine may launch narrow jets along the rotation axis. If those jets break out of the star, they can produce a gamma-ray burst visible across enormous distances. This is where WR104's old Death Star reputation entered the story, because if a gamma-ray burst were produced and pointed toward Earth, that would matter much more than a normal supernova at the same distance. But an ordinary supernova and a gamma-ray burst are not the same thing. This distinction is very important. WR104 becoming a supernova is a reasonable future expectation for a massive evolved Wolf-Rayet star. WR104 producing a long gamma-ray burst aimed at Earth is a much more specific and uncertain scenario. It requires the right internal rotation, the right collapse conditions, the right jet formation, and the right alignment. Many massive stars explode without producing gamma-ray bursts. Many Wolf-Rayet stars are not thought to have enough remaining spin by the time they die, because powerful winds can carry angular momentum away. The star may be stripped, but stripped alone is not enough. Newer observations have made the alignment question calmer. The dust spiral once looked almost face-on, which raised the possibility that the system's axis might point toward us. But later spectroscopic work indicates the actual orbit of the central stars is tilted away from our line of sight by several tens of degrees. That makes a directly Earth-facing jet less likely if a gamma-ray burst ever formed. It does not answer every question about the system's three-dimensional geometry, but it strongly softens the old fear. WR104 remains a fascinating future supernova candidate, not a confirmed cosmic weapon aimed at bedtime. So, could WR104 become a supernova? Yes, in the broad and careful sense. It contains a massive evolved Wolf-Rayet star, and that kind of star is widely expected to end in core collapse. The exact timing is unknown. The exact type of explosion is uncertain. The remnant could be a neutron star or black hole depending on the core. The surrounding dust and wind would shape the aftermath. The companion star would influence what happens to the system afterward, and the gamma-ray burst possibility, while historically discussed, is not the same as the basic supernova expectation and should not be treated as a certainty. That careful answer is more satisfying than a dramatic one because it lets the science stay intact. The universe is already dramatic enough without needing exaggeration. A stripped massive star, orbiting with a hot companion, producing dust in colliding winds, drawing a spiral in infrared light, and preparing eventually for core collapse is quite enough. We do not need to lean over it with a flashlight and whisper, "Be scarier." It has done its share. The supernova question also changes how we see the pinwheel. The spiral is not only beautiful, it is pre-supernova mass loss made visible. It is the star system shaping the space around itself before the final event. Every dusty turn is a sign that material is already leaving the stars and entering the surrounding medium. If the Wolf-Rayet star explodes, that material may become part of the interaction between blast wave and environment. The final flash will not erase the past. It will run into it. That is a common theme in massive star death. Some stars shed shells before exploding. Some blow bubbles through earlier winds. Some interact with companions. some are surrounded by dense material that changes the light from the supernova. Astronomers can sometimes reconstruct the final years or centuries of a star's life by studying the material around the explosion. In WR-104, we are lucky enough to see the mass loss before the end. We're not only waiting for a possible supernova, we're watching part of the preparation. From Earth, that preparation is delayed by distance. The light we see now left the system thousands of years ago. It is possible in the strict sense that something may have already happened there and the light simply has not reached us yet. This is true for almost every distant object in astronomy. But there is no evidence that WR-104 has already exploded, and the timescales involved make any exact statement impossible. We live with the delayed news of the universe. Stars send updates at light speed, and light speed, while impressively fast, is not instant. Even the cosmos has delivery times. If someday astronomers do observe WR-104's supernova, it would become an extraordinary opportunity. They would already know a great deal about the system before the explosion. They would know about the dust spiral, the binary orbit, the wind interaction, and the surrounding material. That would make the supernova a rare case where the progenitor system had been studied in detail beforehand. Usually supernova progenitors are difficult to identify. Often, astronomers find the explosion first, and then search older images to see what star was there before. With WR-104, the pre-explosion system is already famous. If it ever went supernova within the era of modern astronomy, scientists would learn an enormous amount. That does not mean anyone should wish for it in a casual way. A supernova is the death of a star, and although stars do not have feelings in the human sense, there is still something solemn about the end of such a long physical process. The same system that draws a spiral would be transformed. The dust plume would be blasted, illuminated, overtaken, and reshaped. The companion's future would change. A remnant would form. The old pinwheel would become part of a new expanding structure. Beauty would not disappear exactly, but it would change form. For now, WR-104 remains in the before. That is what makes it so valuable. We can study the massive star while it is still losing mass. We can watch the wind collision still making dust. We can measure the spiral still turning. We can examine the system before the final collapse has rewritten everything. In astronomy, the before is often as important as the event. The explosion may be brief, but the preparation lasts far longer and contains the clues to what the explosion will become. There is also comfort in the fact that WR-104's future is not our immediate problem. The star is distant. The timing is unknown and likely not human. The gamma-ray burst alignment concern has been reduced by newer measurements. The ordinary supernova expectation is scientifically important, but not a reason to lie awake. If anything, WR-104 gives us a chance to think about stellar death without panic, to see it as part of the galaxy's long recycling process. A massive star dies, but in dying it sends material outward. Its winds and explosions seed space with heavier elements. Its remnant joins the population of dense objects. Its companion may continue the story. The galaxy changes slightly, because one star lived the way massive stars do. That idea brings the supernova question back to the dust. The dust is not separate from the star's ending. It is part of the mass the star has already given away. Some of it may be destroyed by the eventual explosion, some may survive, some may be pushed outward, mixed, heated, or broken apart. New dust might even form in the aftermath as supernova ejecta cools. Massive star death is not only destructive, it is chemically creative. It rearranges matter, drives shocks through space, and helps enrich the clouds from which later stars and planets may form. So the answer is yes, WER-104 could become a supernova, and in the long story of the system, it likely will. But that answer should be held gently, with all its surrounding details, not soon in any way we can schedule, not necessarily with a gamma-ray burst, not necessarily pointed at Earth. Not with every detail known in advance. It is a future written in core physics, wind history, binary interaction, and chance geometry. The pinwheel shows us the preparation, not the final page. It is interesting because it teaches us how massive stars approach their endings. The spiral is not a countdown clock in any simple sense. It is a record of wind, dust, and orbit. The coming explosion, whenever it happens, will be part of that same story, the next transformation of matter already moving outward from the central stars. And that naturally leads to the most dramatic question still attached to WR104, the one that made it famous far outside ordinary stellar astronomy. A supernova is one thing. A gamma-ray burst is another. The gamma-ray burst question is the part of WR104's story where the beautiful spiral becomes, at least for a while, a little less relaxing. Not because the star suddenly changes what it is doing, and not because the dust begins behaving badly, but because the human imagination notices a line, follows it outward, and wonders where that line might go. A Wolf-Rayet star can end its life violently. Some massive stripped stars can, under the right conditions, produce gamma-ray bursts. Gamma-ray bursts can be beamed. Beams have directions. And when WR104's pinwheel first appeared to be facing us almost directly, the obvious question arrived quietly, then rather loudly. What if the beam pointed toward Earth? That is the question that gave WR104 its uneasy public reputation. A distant star system with a perfect spiral was strange enough. A distant star system with a perfect spiral that might one day send a powerful burst of radiation in our direction sounded like something the universe had written after watching too many disaster films. It is not hard to understand why the nickname caught on. The Death Star label was dramatic, simple, and memorable, and those three things travel much faster than careful scientific uncertainty. But the real story is not that WR104 is a cosmic weapon. The real story is how an honest scientific concern became tangled with a beautiful image, and how later observations made the picture calmer, safer, and more interesting. A gamma-ray burst, or GRB, is not just a bright supernova. It is a short, intense flash of high-energy radiation, usually associated with some of the most extreme events in the universe. There are different kinds of gamma-ray bursts, but the type relevant to a massive Wolf-Rayet star is the long-duration kind, often linked to the collapse of a very massive stripped star. In some models, when such a star's core collapses into a black hole, a powerful engine forms at the centre. Material falls inward, energy is released, narrow jets may punch outward along the star's rotation axis. If those jets break through the star and point toward us, we see a gamma-ray burst. The important word there is if. In fact, several ifs are stacked on top of one another like a very unstable tower of teacups. The star has to collapse in the right way. It has to keep enough rotation in its core. It has to form jets. The jets have to escape. The beam has to be aimed at Earth. The burst has to be energetic enough and close enough to matter. WR104's old fear depended not on one certain fact, but on a whole sequence of uncertain conditions lining up together. That does not make the question foolish, it makes the question conditional. Gamma-ray bursts are dangerous in principle because gamma rays carry enormous energy. If a strong nearby burst were aimed directly at Earth, the problem would not be that the gamma rays would burn the ground like a giant heat lamp. Our atmosphere is very good at absorbing high-energy radiation before it reaches the surface. The more serious issue is chemistry high above us. A powerful burst could change the chemistry of the upper atmosphere, damaging the ozone layer that protects life from harmful ultraviolet radiation. That could have long-term biological effects. So when scientists discuss GRB hazards, they're not imagining a laser beam slicing mountains in half. They are thinking about atmospheric chemistry, radiation exposure, and ecological stress over time. It is less cinematic but much more real. WR104 entered that discussion because it is relatively nearby on galactic scales, and because it contains a Wolf-Rayet star. Relatively nearby does not mean next door. We're still talking about thousands of light years. That distance is enormous by human standards. But gamma-ray bursts are so powerful that astronomers naturally ask whether a close one, if directed toward us, could affect Earth. The first resolved images of WR104's dust spiral made the question sharper, because the spiral looked almost face-on. It seemed as if we were looking straight down the system's axis, like looking into the centre of a turning wheel. If the dust spiral and the stellar orbit shared the same plane, then a face-on spiral would suggest the orbital axis pointed roughly toward us. If the star's rotation axis lined up with that orbital axis, and if a future GRB jet followed that rotation axis, then the jet might also point toward us. That chain of reasoning is easy to follow. It is also full of assumptions. At each step, nature has room to do something different. The dust plume may not lie exactly in the orbital plane. The orbit may not match the star's spin. The star may not produce a GRB. The jet, if it exists, may have a narrow opening angle and miss us. The distance and energy may reduce the effect. A good scientist sees the chain and asks for evidence at every link. For a while, the most visible evidence was the spiral itself. The pinwheel looked beautifully round and regular, and that gave the impression of a nearly face-on system. The early measurements suggested a low inclination, which means a viewing angle close to looking down on the orbit rather than across it. The worry followed naturally. If we were looking down the axis, maybe we were sitting in the path of a future beam. That possibility was never a prediction, but it was enough for headlines. A star system that might explode someday is interesting. A star system that might explode someday in our direction is irresistible to the louder parts of the internet. The calmer scientific view always had more caution. Wolf-Rayet stars are plausible supernova precursors, but only a subset of massive star collapses produce gamma-ray bursts. Long GRBs are often associated with special conditions, including rapid rotation and low enough mass loss that the core retains angular momentum. Wolf-Rayet winds can remove angular momentum from a star, making a GRB less likely in some cases. Metallicity, binary interaction, internal mixing, magnetic fields, and core structure all matter. The outside of the star does not tell us everything about the core. So WR104 was never simply a GRB waiting to happen. It was a possible candidate in one scenario, with many unknowns. Then came the new twist. Spectroscopic observations of WR104's central binary suggested that the orbit is not as face-on as the dust spiral alone seemed to imply. By watching how spectral lines shift as the stars move, astronomers can measure radial velocity, the motion toward and away from Earth. If a binary orbit were perfectly face-on, the stars would mostly move side to side from our point of view, and their radial velocity shifts would be small. But the measured shifts indicated a more tilted orbit. Later work supported an inclination around several tens of degrees, roughly in the neighbourhood of 40 degrees, with uncertainty but clearly not the nearly straight-down view suggested by the simple pinwheel image. This is the part that made Earth safer in the WR104 story. If the actual orbital plane is tilted, then the axis perpendicular to that plane is not aimed directly at us. And if any future jet followed that axis, it would likely miss Earth by a wide angle. That does not prove every possible detail of the system, because the geometry is still complicated, but it weakens the old direct aim scenario significantly. The Death Star image depended heavily on alignment. Tilt the system away, and the beam no longer points at us. The frightening straight line becomes an off-center line, and off-center matters very much when dealing with narrow jets. There is a funny kind of relief in that. The same system that once looked like a neat target now appears to be a more complicated three-dimensional structure. The dust spiral still looks nearly face-on in high-resolution images, but the stellar orbit seems more inclined. That means the beautiful pinwheel was hiding a geometric puzzle. How can a dust plume look so face-on while the orbit of the stars is tilted? Are we seeing only the brightest part of a wider structure? Does dust scattering or opacity make the spiral appear more circular than it truly is? Is the wind collision region shaped in a way that separates the visible dust from the simple orbital plane? These are the questions astronomers now get to explore. Earth becomes less worried, and science becomes busier. That is a rather good trade. The newer picture also teaches us not to trust a single view too completely. A spiral on the sky is a projection. It is a three-dimensional structure flattened into an image. Projection can fool the eye. A tilted object can appear more circular if its brightest regions are arranged in certain ways. Dust can hide one part of the flow and reveal another. Scattered light can emphasize one angle. Infrared glow can trace temperature and density, not just shape. Spectroscopy provides a different kind of information, one based on motion along our line of sight. When images and spectra disagree, the answer is not to choose the prettier one. The answer is to build a better model. That is exactly why WR104 remains valuable. It is not just safer than the old nickname suggested, it is also more scientifically demanding. The dust spiral says one thing about the visible plume. The stellar spectra say another about the orbit. Photometric changes, including possible dust-related dimming and scattering effects, add another layer. Hydrodynamic models of colliding winds add another. The system is not a simple flat wheel. It is a binary star engine, a shock cone, a dust factory, and a projection puzzle all at once. The Death Star nickname collapses all of that into fear. The science opens it back up into structure. It also helps to remember that a gamma-ray burst beam is not a broad glow filling half the galaxy. It is expected to be narrow, which is both what makes it dangerous if you're inside it and what makes it unlikely to hit any particular target. Imagine a flashlight beam in a vast dark field. If the beam points directly at you, you see it clearly. If it points a little away, you may see nothing at all. A GRB jet is far more extreme than a flashlight, of course, and not something anyone should use to look for lost keys, but the directional idea is useful. Alignment is everything. A tilt of several tens of degrees is a major difference. There is still uncertainty about the exact relationship between a future explosion and the current binary orbit. A jet, if formed, would most likely align with the rotation axis of the collapsing star or the Compaq engine, not necessarily with the binary orbit in a perfectly simple way. In many systems, the star's spin and orbit may be related, especially after long binary interaction, but they do not have to be identical. This means even the safer orbital inclination does not let us claim perfect knowledge of the future. It does, however, remove the most straightforward reason for thinking Earth sits directly in the line of fire. Science often improves safety estimates not by proving impossibility, but by showing that the scariest simple geometry is not the best current description. The time factor adds more calm. WR104's Wolf-Rayet star is late in its life, but late for a massive star does not mean tomorrow. Its supernova could occur in the future on timescales far beyond ordinary human planning. Thousands or hundreds of thousands of years are often discussed for such evolved massive stars, but the exact timing is unknown. We are not watching a countdown, we are watching a stage of stellar evolution. A late-stage star is like an old mountain glacier in one sense. It is moving toward change, but not on a schedule convenient for human nerves. It is also possible that the star will explode as an ordinary stripped envelope supernova without producing a GRB at all. That may even be the more likely broad expectation. A supernova would still be scientifically spectacular, but at WR104's distance and through the dust of the Milky Way, it would not automatically be harmful to Earth. The GRB scenario is the special case. The safer tilt mainly addresses that special case by making an Earth-directed beam less plausible. So the careful bedtime version is this. WR104 may someday go supernova, but the feared Earth-facing gamma-ray burst is not supported by the newer geometry. That sentence is much less dramatic than Death Star. but much better for sleeping. The atmosphere of fear around WR104 also shows how astronomy stories can become distorted when rare events are discussed without probabilities. Gamma-ray bursts are real. Massive stars can collapse. Some collapses launch jets. WR104 is a massive binary with a Wolf-Rayet star. Those facts are all interesting, but the leap from those facts to this star will harm Earth skips the uncertainty that gives the science its shape. It is like saying that because lightning exists and clouds exist, every cloud is coming personally for your umbrella. A little caution is healthy. A little scale is healthier. Scale is especially important in deep space. The Milky Way is vast. WR104 is thousands of light years away. Its light takes thousands of years to reach us. Even if the system has already changed since the light we now observe left it, we would not know until that later light arrives. That delay can sound unsettling, but it's simply how astronomy works. Every distant star is a message from the past. We live inside a universe where news travels at the speed of light, and the speed of light, while famously fast, still has a long commute across the galaxy. If WR104 did one day produce a GRB not aimed at us, it could still be an extraordinary astronomical event. Instruments might detect high-energy radiation from the direction of Sagittarius, depending on the beam orientation and emission. Other wavelengths could follow as the supernova expands. Astronomers would study the aftermath and compare it with decades of earlier data on the pinwheel, the orbit, the dust, and the winds. That would be a scientific treasure. It would let researchers connect a known pre-supernova Wolf-Rayet binary to its final explosion. In that sense, WR104 is not frightening, because it might one day change. It is valuable because we already know so much about its before. The new twist about inclination does not make WR104 less beautiful. It makes the beauty more honest. The spiral is still there. The dust is still forming. The winds are still colliding. The central stars are still circling. But now the system refuses to be reduced to a simple face-on diagram. It says, in effect, "You thought you knew my angle. Look again." And astronomers do exactly that. They take more spectra. They revisit older photometry. They build models where dust can scatter light, obscure stars, and form in a tilted shock cone. They ask how a structure can look one way in infrared images and another in orbital motion. This is the quiet work behind the headline. For us, listening from a safe and sleepy distance, the lesson is gentle but useful. A scary nickname is not the same as a measured risk. A dramatic possibility is not the same as a prediction. A beautiful image is not the same as a complete three-dimensional map. WR104 was once called a Death Star because the early geometry seemed to raise a plausible concern. Newer observations have made that concern much weaker by showing that the orbit is tilted away from a direct Earth-facing alignment. The star remains extreme, but extreme does not mean aimed at us. There is something reassuring about the way the story changes through evidence. The universe did not become safer because we wished it so. It became safer in our understanding because instruments measured the system more carefully. Spectral lines shifted, data accumulated, models improved. A frightening simplification gave way to a more nuanced picture. That is one of science's quiet comforts. It does not remove all uncertainty, but it can remove unnecessary fear. But R104 still has a future written in massive star physics. Its Wolf-Rayet star may eventually collapse. Its companion will continue its own massive life. The dust spiral will keep expanding turn by turn as long as the system keeps producing it. One day the pattern may be interrupted by an explosion, reshaped by a blast wave, or scattered into the surrounding galaxy. But from Earth, the old idea of a beam pointed straight at us no longer fits the best current evidence. The pinwheel is not a target. It is a tilted, complicated, dust-making system, seen from one particular place in the Milky Way. So the gamma-ray burst question does not end with panic. It settles into perspective. Yes, GRBs are powerful. Yes, massive stars can die violently. Yes, WR104 was once considered unsettling because its spiral looked nearly face-on. But the new twist is that the central orbit appears tilted away from us, making the feared alignment much less likely. The object remains a rare and useful laboratory, not a bedtime threat. It's a reminder that the most dramatic interpretation is not always the most accurate one, and that sometimes looking more closely turns fear into curiosity. That shift from fear to curiosity is perhaps the best way to carry WR104 forward. The system still has mysteries, but they are better mysteries now. Not, will this star harm us? But, how does this tilted binary produce such a face-on-looking spiral? Not, is this a weapon? But, how do colliding winds, dust and projection combine to fool the eye? Not, should we worry, but, what can this rare system teach us about massive stars before they die? Those questions are calmer, richer and much more useful. And as the old Death Star label fades into the background, what remains is the pinwheel itself, still turning in infrared light, still carrying carbon dust outward, still preserving the rhythm of two massive stars at its centre. It is dangerous only in the broad way massive stars are dangerous, powerful, brief and transformative. It is beautiful in the practical way physics can be beautiful, where motion becomes pattern and pattern becomes evidence. With the gamma-ray burst question placed back where it belongs, not ignored, not exaggerated, but held carefully inside the physics, WR104 becomes a much quieter object in the mind. Not quiet in reality, of course. Nothing about two massive stars throwing winds into each other, making dust in a shock zone, and preparing for some distant final transformation could honestly be called quiet. But quiet in the way we can now think about it. The fear softens, the headline fades, the spiral remains. That may be the most useful lesson WR104 gives us. The universe can be dangerous without being directed at us. It can be beautiful without being gentle. It can be far away and still teach us something intimate about how we understand risk, time, and our own imagination. WR104 sits thousands of light years away in the direction of Sagittarius, hidden from ordinary sight, glowing most clearly in infrared light, and yet its story reaches us as a strange mixture of elegance and force. A pinwheel made by colliding winds, a dust factory beside a dying massive star, a system once feared because it looked aligned with Earth, and later made less frightening by better measurements. That is not just a story about one star, it is a story about how science changes the shape of wonder. At first glance, WR104 feels almost designed to confuse our instincts. The spiral looks delicate. It curls outward with a smoothness that feels almost careful, as if someone had drawn it slowly with a fine brush. But the cause of that spiral is not delicate at all. It is made by hot stars, powerful radiation, supersonic winds, shock fronts, and grains of carbon dust forming where they seem barely allowed to exist. The shape is graceful because the physics repeats regularly. The stars orbit, the winds collide, the dust forms, the material flows outward, the pattern turns again. There is no intention behind it, no hand guiding the curve, and still the result looks almost handmade. That is one of the strange comforts of astronomy. It shows us that order does not always require softness. A hurricane has a shape, though no one would call a hurricane gentle. A spiral galaxy has arms, though those arms contain exploding stars, radiation, black holes, and whole generations of suns being born and dying. A seashell grows in a pattern because biology and chemistry follow rules, not because the ocean hired a designer with excellent taste. WR104 belongs to that same family of natural forms. Its beauty is not separate from its violence. Its beauty is the visible trace of that violence organized by motion. This is where danger becomes more interesting than fear. Fear wants a simple answer. Is it safe or not? Is it coming for us or not? Should we worry or not? Science often answers with something less dramatic but more useful. Here is the distance. Here is the system. Here is the uncertainty. Here is the newer measurement. Here is what would need to happen. Here is why the most alarming version is unlikely. That may not make a good movie trailer, but it is much better for a mind trying to rest. WR104 teaches us that danger in space must be understood through scale, probability, alignment, and time. Without those, every extreme object becomes a monster. With them, it becomes a subject. There is no shortage of extreme objects in the universe. Black holes tear matter into disks of heat. Neutron stars crush more mass than the sun into the size of a city. Supernovae scatter stellar material at huge speeds. Gamma-ray bursts can be seen across billions of light-years. Massive stars live fast and die hard, as if the universe gave them a short contract and an unlimited lighting budget. But these objects are not arranged around Earth like threats in a storybook. They are part of a galaxy full of physical processes. They do what matter and energy do under extreme conditions. Our task is not to panic at them, but to understand them. WR104 is particularly good at teaching that because it once looked so personally unsettling. The spiral appeared nearly face-on. The Wolf-Rayet star might someday explode. Gamma-ray bursts are beamed. Human brains are very good at connecting dots, sometimes a little too good. Before long, the pinwheel became a target in the imagination, but the newer picture is more complicated and more calming. The orbit appears tilted away from a direct Earth-facing alignment. The dust spiral and the stellar motion do not line up in the simple way early assumptions suggested. So the object did not become less fascinating. It became less threatening and more scientifically demanding. That is a lovely exchange. Less fear, more mystery. Fewer alarming headlines, more careful geometry. The universe did not change, but our understanding did. That is one of the quiet powers of observation. A better spectrum can take the sharp edge off a worry. A longer set of measurements can turn a dramatic nickname into a historical footnote. More data does not make the cosmos boring. It makes the wonder sturdier. It lets us marvel without being dragged around by the loudest possible interpretation. Deep time is the third part of the lesson, and perhaps the hardest one for our human minds to hold. WR104 is far away, so every photon we receive is old news. The spiral we study is not a live video feed. It is light that crossed thousands of years of space before arriving at our telescopes. The system may continue much as we see it, or it may have already changed in ways whose light has not reached us yet. This is true of the night sky in general, but WR104 makes it feel especially vivid. We are watching a delayed spiral, a past motion made visible now. That delay can feel strange, but it is also part of the calm. Space does not deliver everything instantly. The galaxy is not a room where every lamp turns on at once. It is a vast structure where information travels at the speed of light, and even light has to take the long road. When we look towards Sagittarius, we are receiving messages that began their journey long before our modern world existed. Long before telescopes could resolve the pinwheel, long before anyone named Wolf-Rayet stars, long before anyone worried about gamma-ray bursts, the light was already crossing interstellar space, carrying the dust pattern patiently toward us. This gives WR104 a double timescale. At the centre, the stars orbit in less than a year. That is fast enough for astronomers to watch the spiral change across repeated observations. But the light from that motion takes thousands of years to reach us. And the star's future supernova may belong to a timescale much longer than any human plan. Months, millennia, and stellar endings all sit together in one object. A 241-day orbit written inside a light travel delay of thousands of years, inside a life cycle of millions of years. It is a clock inside a clock inside a clock, and none of them care whether we remember to charge our phone. Deep time can make human life feel small, but not necessarily in a sad way. It can also make the present feel more specific. Here we are, in this brief little window, able to receive the old infrared glow of dust around a massive binary star. We happen to live after the invention of telescopes, after spectroscopy, after infrared detectors, after the mathematical tools needed to model colliding winds, and after enough patient observing to see the spiral turn. For most of human history, WR104 was simply hidden. Not absent, not unimportant, but unseen in its true form. Now it is part of our map of the galaxy. That is a remarkable privilege when you think about it gently. We are not large compared with the Milky Way. We are not ancient compared with stars. We are not powerful compared with a Wolf-Rayet wind. But we are curious, and curiosity is a kind of reach. It lets a small species on a small planet build instruments that notice a dust spiral thousands of light years away. It lets us ask what makes the dust, how fast the stars orbit, what angle the system presents, what future might await it, and whether early fears were justified. Curiosity does not make us central, it makes us connected. WR104 also teaches us that the universe often hides important things in forms we first notice for their beauty. The spiral catches the eye, but the eye is only the beginning. Behind the image is a binary orbit. Behind the orbit are stellar winds. Behind the winds is the evolution of massive stars. Behind the dust is carbon forged in stellar interiors. Behind the future supernova is the long recycling of matter through the galaxy. A pretty picture becomes a doorway. That is true of so many astronomical images. They're not just decorations for calendars or wallpapers for sleepy laptops. They are evidence with colour and shape. The dust itself may be the most humble teacher in the whole system. Tiny grains, almost absurdly small compared with the stars that create them, reveal the movement of objects we cannot directly separate. They glow in infrared, outline the spiral, and preserve the recent history of the binary. They form in difficult conditions, drift outward, cool, fade, and eventually mix into the wider galaxy. Some may be destroyed, some may survive, some may one day become part of a cold cloud where new stars begin. A grain of dust near WR104 is not dramatic by itself, but in great numbers those grains make the system visible. Small things gathered together can reveal enormous truths. A comforting thought, especially for anyone who has ever felt like a small thing in a large universe. The companion star also deserves its quiet respect. Without it, the Wolf-Rayet star would still be extreme, still hot, still windy, still headed toward a dramatic future. But the spiral would not be the same. The companion's wind helps create the collision zone. Its orbit helps turn that zone into a rotating source. Its presence may even help the chemistry of dust formation. WR104 is a reminder that relationships shape outcomes, even among stars. A single massive star can be powerful, but two massive stars together can create something neither would make alone. In astronomy, companionship is often not sentimental, it is structural. That idea echoes far beyond WR104. Binary stars shape supernovae. They can create compact objects. They can exchange mass, strip envelopes, spin one another up, and alter final fates. Many of the universe's most interesting objects come from interactions rather than isolation. WR104's spiral is one clear visible example of that larger rule. The universe is not a collection of separate things merely sitting near one another. It is a web of interactions. Gravity, radiation, wind, collision, chemistry, motion. The spiral exists because those interactions line up. The old danger story, then, becomes one layer in a larger lesson about perspective. From one angle, WR104 looked like a possible threat. From another, measured more carefully, it became a tilted, complicated, dust-making laboratory. From one wavelength, it may look faint or obscured. In infrared, it becomes a glowing pinwheel. From one human timescale, it seems frozen. Across observations, it turns. From one headline, it is frightening. Through science, it is understandable. None of these views is the whole object by itself. WR104 teaches us to keep changing the lens. That may be useful far beyond astronomy. Many things look simpler, scarier, or more certain when seen from only one angle. A little more information can change the shape of the story. A little more patience can reveal motion. A little more attention to scale can soften panic. WR104 is a distant star system, but the way we learned about it is very human. We noticed beauty, we imagined danger, we measured more carefully, we revised the story, we kept the wonder, and now, as the night grows quieter around this thought, the spiral can settle into the mind in a different way. Not as a weapon, not as a warning, not as a final answer, as a turning record of two stars in their late, intense lives. One stripped and carbon-rich, one hot and massive, both pouring winds into space. Between them, the gas compresses, downstream, dust forms. The orbit carries the dust-making region around. The grains glow in infrared. The spiral expands, curve by curve, while light from the whole process begins its long journey across the Milky Way. Somewhere along that journey, Earth keeps turning. Generations rise and pass. Languages change. Cities grow. Telescopes are invented. Instruments improve. Eventually, a few photons from WR104 arrive at a detector, and people begin reconstructing the hidden dance that sent them. That is deep time made personal, not because the star is about us, but because we are briefly able to understand something about it. For a moment, the distance between a human life and a massive star becomes bridgeable by attention. Beauty, danger, and deep time are not separate themes in WR104. They are braided together by the physics. The beauty comes from the spiral, but the spiral comes from violent winds. The danger comes from massive star death, but the actual risk depends on geometry and probability. The deep time comes from distance and evolution, but the system also changes quickly enough for us to watch its dust move. Everything depends on context. Without context, beauty becomes decoration, danger becomes panic, and time becomes too large to feel. With context, the object becomes understandable, and understanding is one of the gentlest forms of awe. It is worth returning once more to the name. WR104 is plain, practical, and catalogue-like. It does not sound like a mythic object. It sounds like something filed neatly in a drawer. Yet behind that modest label is a system that looks like a glowing spiral, manufactures dust in hostile conditions, may someday explode, and once made people wonder whether a beam of radiation could be aimed at Earth. That contrast is almost funny. The universe often hides astonishing things behind very ordinary names. WR104. A few letters and numbers, a pinwheel in Sagittarius, a massive binary nearing the end of one star's life. A lesson in not judging a cosmic object by its catalogue entry. As this journey reaches its gentle close, it may help to picture the spiral one last time, but slowly. Not as a static image on a screen, and not as a threat pointed across the galaxy. Picture two hot stars at the centre, too bright and close to separate easily. Around them, winds rush outward. Between them, the collision zone curves like an invisible seam. Carbon-rich gas cools enough for dust to begin. Tiny grains grow, warm and glow. The stars orbit again, and the dust trail bends. Older dust moves outward while new dust forms nearer the centre. The pinwheel turns, not for us, not against us, simply because the laws of nature are doing their work. That is enough. It does not need to mean more than it does. It does not need to be a message or a warning or a symbol placed there for human eyes. Its reality is already rich. A physical system far away, following rules that we can partly understand, creating a form that our minds find beautiful. Sometimes that is the calmest kind of wonder, not the feeling that the universe is speaking directly to us, but the feeling that the universe is understandable at all. So wherever you are listening from tonight, whatever time it is in your small turning place on Earth, perhaps WR104 can leave you with a quieter view of the sky. Above us are not just stars but histories, not just light but old messages, not just dangers but distances and probabilities, not just beauty but physics wearing a shape the eye can follow. The pinwheel star is still there in Sagittarius, hidden from ordinary sight, turning through old light, sending its dusty record outward into the galaxy. If this slow journey through the spiral has brought you a little calm, a little curiosity, or simply a softer way to think about the dark above, I would be ever so grateful if you liked the video, subscribed, or shared this quiet corner of science with someone who might enjoy drifting through the universe at bedtime. WR104 may be fierce, hot, dusty and strange, but from here, across thousands of light years, it gives us something peaceful to hold. The knowledge that even in the most extreme places patterns can form, fear can become understanding, and time can turn violence into a spiral. Sleep well, fellow traveller, wherever you are beneath the sky tonight. And if your thoughts wander before rest finally finds you, let them wander gently towards Sagittarius, where two massive stars keep circling, where dust keeps forming against the odds, and where a perfect-looking spiral reminds us that the universe is often most beautiful when we take the time to understand why.